plots. We discuss plots. Plots of automata. These are well, non-formally speaking, we send to Automaton words of different words of different lengths. Well, send all words. Map put into the correspondence toward the points between 0 and 1 in that manner, and obtain a point set in the unit square, and after that we take a closure of that set and consider that closure, and we prove that the measure could be 0 only or 1, and this was the starting, so to say, point of our investigations. We discussed some theorems, and now I will show you the plots, how they look like. And the very interesting thing is that there are in their plots, there are some pronounced straight lines. Do you see them? I will now increase the length of input words and hope that you see these pronounced straight lines in the plots. These are real plots. The program is working now. And you see these pronounced straight lines in the plots. Look at these lines more attentively. For example, this line, it goes here, then it starts again here, and it goes here, right? And this line, it goes here, right? Then we can see that it goes here, and again here, etc. So if we glue together this side with that side, we obtain, well, a tube. Then we glue together this side with this side, and we obtain a torus, right? We obtain a torus. What will be these straight lines? They will be winding of torus. They will be winding of torus. And this is not occasional. This is a very important thing about these automata maps. Well, now, well, actually, when we do these mappings, and consider the plots on the torus, we actually consider the mappings which are performed by our automata, by our automaton function, which we perform over characters. So we put into the correspondence to every rational Piatic integer its character, and this way, right? And then we calculate the image, the automaton function of this rational Piatic integer, and consider it a character. This is how we put into the correspondence to the automaton map the map which it performs on characters, and thus we obtain a plot on the torus rather than on the unit square. And this picture is much more interesting for us due to future applications. So the automata, which we consider this automaton, limit plots of finite autonomous automata, they will be constants. They will be look like that. This is in the unit square, and this is on the torus. This is a constant 2/7. For example, P2, P equal to 2. For example, for affine functions, we will have windings of torus. Do you see these windings of torus? And this is how it will look on the torus. This is in the unit square, and these are in the torus, on the torus. So this is this map, this function. And actually, we deal with these maps when we are speaking about these maps on the torus. Okay, we will discuss these things, and it can be shown that if we have an automaton function of a finite automaton, and if this function, if g is some other function c squared, so just a function, real function, which is 2 times differentiable and has continuous second derivative, and let the graph of this function completely lie in the limit plot. Limit plot of the automaton is the set of all limit points of the plot, of all accumulation points of the plot. It is clear that if there are lines in the plot, they all will be in the limit plot, because there must be limit points. And the graph, if it lies completely in the plot, then this will be necessarily the graph of this function, of a fine function, and nothing else. This means that no other smooth curves rather than winding of torus can occur in automata automata plots on the torus or on the unit square. So this is a finite number of pairwise distinct torus windings like that or like that. This is how we look this is how we look the limit points in this case, the limit points. So there will be different winding of torus, and then it is this goes torus link of torus nodes. The multidimensional analog of the theorem for finite automata holds as well. It's difficult to show this in many dimensions. It's a very a little bit complicated picture, but it also holds. And what we will do now? We can represent torus. We can represent torus in a three-dimensional map, and in three-dimensional real space by these parametric equations. So this is a rotation of a circle around z-axis, and this is the parametric in cylindrical coordinates. Every winding of this form will have this representation. So in cylindrical coordinates, every winding will have this representation, and the winding wins beta times around z-axis, and absolute value of alpha over around the circle of the torus. So a physical meaning of this one is frequency. And what is this? This is because this corresponds to this one. Well, this is of course this is of course phase shift. So we have a frequency and we have a phase. Actually, we have a wave. This will be the most important in our considerations. Well, this theorem is give a complete answer if we have a function, if we have a finite automaton function So finite means A and B, they will be Piatic integers. How many they will be these torus windings in a torus links? This is how many. Then this is multiplicative order of P modulo this number, modulo this number. So we can always calculate this. And now this is what they come from. This where they come from. This winding of torus. They come from minimal automata. I recall that minimal automaton is an automaton which contains no other subautomata than itself. So on the diagram, of this automaton is completely connected. This is a diagram of the automaton, and this is not minimal because it has that one is minimal subautomaton, but look. This subautomaton, if we will consider then these limit plots, the functions which correspond to this automata are different. For example, if we take S0 as initial, we will get this function. If we take S1 as initial, we will get this function, automaton function, and this. But the limit plots are the same. This is the common limit plots. This is very important. Formally looking different. Automata functions, automata maps have identical limit plots, and later we will deal namely with limit plots. The next step. This automaton is not minimal. It has two subautomata, and these subautomata, these both are minimal. This one of automaton corresponds to multiplication by 3, and the next one corresponds to multiplication by 5. My running example is P2. Yes, and this is this is what this is how these functions are looking, limit plots are looking on the torus, This is how they look on the torus. Well, this is well, so to say, the end of theoretical part, and now we are going to physics. Now we are going to applications to physics, and now we will I will explain how this the theory can be applied to physics, namely to quantum theory. To quantum theory. Then Walovich postulates in his name. This one of the physicists, one mathematical physicist who started developing Piatic mathematical physics. In his numerous papers, books, talks, etc., he announced certain postulates that only rational numbers can be observed, irrational numbers cannot, distances smaller than Planck lengths cannot be measured, and fundamental physics laws should be invariant with respect to the change of the field. And another physicist, Gerard 't Hooft, a Nobel Prize winner. It's a known physicist. He developed also a theory of cellular automaton interpretation of quantum mechanics, and he wrote that it may be that at most basic level there are no randomness in nature. Every significant event in our universe takes place for a reason. It was caused by the action of physical law and not just by chance. I will try to apply these two ideas and to show that there are some mathematical models which are consistent with these two types of postulates, with Walovich postulates, and with 't Hooft postulate. Know that the notion of causality is completely based on the notion of time, because it means that cause cannot happen, that effect cannot happen before that cause has happened. But time is a totally ordered countable set. Why countable? If we want to follow Walovich postulates and we deal with rational numbers, they are only countable. And if time is a totally ordered countable set, then there are only two types of totally ordered countable set. Continuous time, when the ordering of elements is dense, and discrete time, if there are given two time moments, there are not more than finitely many other time moments lying in between. But the time which is countable, totally ordered countable set, it must be order isomorphic to a subset of rational numbers. So this is a well-known theorem from mathematics, now we will, in both cases, discreteness assume that space-time should somehow be quantized, and continuous models based on the assumption that any spatial interval can be divided into smaller intervals ad infinitum, and whereas this discreteness assumes that indivisible values which we append one to another can also be increased ad infinitum. Can we somehow agree with these theories? I recall the definition of causal functions over discrete time from the theory of systems. These are just mappings of infinite strings of causes to infinite strings over other alphabet, the elementary effects. These are elementary causes. These are elementary effects. So the function is causal if there is a sequence such that what happens that causes depends only on the effects which has already happened. And we have seen this picture at the very beginning of the lecture. So you see that this is just a definition of the automaton mapping. This is just a definition of the automaton function. So causal functions are exactly automaton functions, are exactly automata functions for automata whose input and output alphabets are I and B, and we will, of course, consider that these automata are action over finite alphabets. Okay, this is as only rational numbers couldn't be observed, the domain and range of functions representing physical laws which can be experimentally verified must be the field of rational numbers, according to ideas. But in order to this to be invariant with respect to the change of a number field, a restriction of any such functions to a bigger field must be the same, irrespectively of what field is. Whether it is, but there are only few bigger fields, not very few, infinitely many, of course, but there are bigger fields which contain Q. I mean, complete metric space. There are only QP, the field of Piatic, numbers and R, the field of real numbers. So the restrictions must be the same. The restriction must be the same. But if we want that these functions which we deal with must be causal, then they must be defined. They must be defined. All these functions to be consistent with Walovich postulate. All these functions must be the same when we consider it on the, so to say, common space. Their common space. So the restriction to every such space of a causal functions must be the same. So from one hand, they must be expandable to the whole set, to the whole field R, and must be expandable to ZP to be causal functions, so to be automatic functions. So we can now summarize the consistency condition. A continuous real function, which is consistent with both Walovich postulates and Hooft causality postulate, must share the following properties. The restriction of this function must be a causal function of a discrete time n0, 0, 1, 2, 3, etc. And the restriction must satisfy a Piatic Lipschitz condition with a constant 1 to be automatic. As n0 is dense as ZP, then from here it follows that there is a unique extension of this restriction to this function, which is one Lipschitz with respect to the Piatic metric. But to be invariant with respect to change of the field, this function must act on this set, the common part of this and this, of all rational Piatic integers, exactly as that function acts. That the restriction on rational Piatic integers must coincide both with this function and with this function. That's all. And continuity implies that this map rational integers, Piatic rational integers to Piatic rational integers. And the first question, of course, is are there functions? Do there exist functions which are consistent with all these postulates which satisfy this condition? And the answer is we define the three types of consistency. We call a continuous means with all these postulates if it maps Piatic integers to Piatic integers for all P, and it is this one Lipschitz with its restriction to this rational Piatic integers is one Lipschitz with respect to Piatic metrics, and if this holds for all prime P, this is called completely consistent. We call this function P consistent if it holds for only for some P, and if it calls for a set of P, we call this P consistent, but P large. So these are three classes of functions. What are these functions? The first question. These are these functions. This is complete answer that for a complete characteristic of completely consistent functions. So these functions are of this form. These are polynomials. Rational coefficients with rational coefficients under this form. This is least common multiply, and this is a binomial coefficient. This is a binomial coefficient. Okay, this is answer, of course, and so such functions exist, and this is the good class of functions, because this means that they are causal with respect to any alphabet. We can consider these functions as automatic functions for any type of alphabet. We can take any prime p or composite p as the number as the cardinality of the alphabet of input elementary reasons and any alphabet as elementary effects. This is the answer. And what is also interesting, every function, every function on a real function on a real segment which does not contain integers can be uniformly approximated by these functions. So experimentally we cannot determine whether we deal with this polynomial or with some other real functions. And more interesting, any causal function can be uniformly approximated with respect to Piatic metric by these functions. So we also cannot determine, even we know how to measure on a Planck scale, on the Planck scale distances, where we deal, because we usually measure with some error, whether we deal with this function or with some other function, because these type of functions uniformly approximate both real functions and one Lipschitz functions with respect to both metric, and the approximation is uniform. This is what should be stressed. So I already mentioned these functions which belongs to the class CP when P is fixed. And I already mentioned in the beginning these functions. So I finish this, and now I will show the next theorem. So if we have an automaton function from this class, so the finite automaton functions, because we spoke of arbitrary automaton functions, not necessarily having finite number of states or infinite number of states, but what are the automata functions which correspond to finite automata? If this function is differentiable both over real numbers and Piatic numbers, and if its derivatives with respect to both metrics coincide or here, and are continuous, then this function is necessarily affine. This function is necessarily affine. So finite automata give only affine functions, and affine functions are exactly the functions which produce, so to say, waves on the torus. And actually the observer, if we do experiments with the system and obtain experimental points and measure the experimental points, the clustering of experimental points with respect to real metric, he will obtain interference pictures. This is what physically this theorem means. Moreover, the hologram property of these functions, the functions which belongs to which are continuous both with respect to Piatic and real metric, and if we have two functions like this, and if they agree, if they are equal one to another on some interval, whatever small it could be, then they are equal everywhere. So the behavior of on an arbitrarily small interval completely defines the behavior on the whole real line of these functions. So it resembles as if a small piece of plate, a small containing hologram can reproduce the whole hologram. And there are also results like this, that every continuous functions can be uniformly approximated by these functions. All continuous functions even on the whole line, which vanishes at infinity, can be uniform. Sorry?
Lo único que me hicieron
Question. No questions. What the problem? Sorry, questions or what? Sorry, what's the problem? Do you hear me? Hello, do you hear me? Okay, something can happen because I hear nobody. Do you hear me right now?
I can hear you.
Okay, do you see the screen?
Yes, I do.
Okay. Yep. Okay, then okay, I continue. Okay, so the what is another thing is that any continuous functions can be uniformly approximated by time reversible automata. So that means, but automata which are reversible in time. What does this mean? This may have some relation to the so-called Landauer principle, that the only way to make energy losses in a classical digital computing the smallest possible is to use reversible computation. And the theorem said that we can do it with arbitrary, because we can approximate a function, any continuous function by a reversible automaton. And this is the Landauer's limit. But now, I am going to discuss another important question about ad hoc causality postulate and the randomness. And the answer is a little bit odd, because if we can, the answer is the randomness depends on how we look at the function, from which side, so to say, from the macro side or from the micro side, with respect to what metric. For example, there is a well-known definition of chaos by Divani. That's topological transitivity. Periodical points must be dense, and F has sensitive dependence on initial conditions. But one-Lipschitz functions are not sensitive to initial conditions. This is because of these one-Lipschitz functions are like this, and therefore they always satisfy every iteration satisfy this condition for all n, but sensitivity means that there must exist some epsilon such that this must be bigger than epsilon for some n. This is of course not. So this means that one-Lipschitz functions are not chaotic, but let us consider the logistic map. The logistic map, this is, for example, of this one, this is polynomial with integer coefficient. So it is a CP function. It is both automatic function for every automaton for each p, and this is continuous real functions. But it is not chaotic with respect. It is chaotic with respect to real metric, but it is not chaotic with respect to Piatic metric. This map is not measure preserving on the P. But for example, for P7, that this P is measure preserving on the invariant ball. This ball is invariant. This ball is invariant with respect to this metric, but it is not topologically transitive with respect to topology, Piatic topology on this ball. And it has zero entropy at a Piatic map. But the same map being considered as a real map has non-zero entropy. So what is this chaotic or not? It depends on the point of view. It depends on the point of view. If you consider it from Planck scale, it is not. If you consider it at macro scale, it is. This is just the recall of Knutson's theorem that a continuous transformation of a bounded metric space is topologically transitive if and only if it is on the space. It is topologically transitive on the subspace of it, dense over its dense subspace. But a rational Piatic integers are dense both in real numbers and in Piatic numbers. So this is just confirms that our view completely depends on how we process the data. If we only can deal with the rational numbers, that to say that either the map is random or chaotic or whatever could it be, completely depends on what metric we are using to determine this chaoticity or this randomness. And the answer be yes or no, and who is right? Both right or both not. So this is so an observer conclusion whether the observational data are chaotic or not solely depends on the metric the observer uses to process the observational data. Okay, and now I very fast switch to this problem which I briefly touched of these windings. Imagine we have an automaton. Imagine we will have an automaton, which this is its state transition diagram, and we are moving along the branches of this tree, and we ultimately will occur finally in a sum of these minimal subautomata. This is how it goes. But look here, for example, a minimal subautomaton, let it be this one. So we P2, we consider this way. After that, we are here. We consider this way. We again are here. We consider this way. So we can get to the minimal subautomaton by many ways. But every pass has a probability. This is a probability 1/3, for example. This is a probability, for example, 1/8, of course, because P is 2. And this is probability 1/32, because these are 35 steps. Look, more important, what are these paths? These paths, they all constitute the prefix code. None of these, if we consider this path from the end to the beginning, none of these words is the prefix of another one. This is it is very important notion within informatics. It's called a prefix code. We will deal with. So on the one hand, we will have the passes which are prefix codes, and on the other hand, we have that all these minimal automata actually they correspond to balls, to Piatic balls, and these are probabilities to enter these balls. Okay, just from this moment, we use term Piatic integer, infinite word over P symbol alphabet, and infinite pass over in state transition diagram as synonyms. So, well, the set, if we have some AB Piatic integers, so this set of all infinite balls which ultimately reach a minimal subautomaton whose limit plot corresponds to this function is empty or constitutes a disjoint union of balls of non-zero radio. Then to this function there corresponds a probability. Because this radius, this is if it is a disjoint union of balls, then it is a measurable set with respect to Piatic probability measure, which is a normalized Hall measure. So we do not distinguish between affine automata which have identical limit plots. We deal only with limit plots. So with pictures which see the observer, And what we proceed with this in mind? What we can now we can assign to every this function. Because to every this function, there corresponds a Piatic, a winding over torus, a complex function, which I showed you recently. So we have this sum over what? Over pairs of rational Piatic integers. So this is a countable. This is a series, and there are only countable many of these indices. So this is the series. These are the series, and this series converges absolutely. And therefore they define a complex valid function. For example, this is function. This is example automaton. This function. What is with probability 1 second we will reach this minimal subautomaton or that minimal subautomaton. So this is to this function. It corresponds that functions which look like a wave function, looks like a wave function. And so in general, we have this one. If we have a time, so to say, time-independent case. And what are these functions? These functions, because these numbers, they constitute this set is countable. So to these functions, we can put into the correspondent, we can put into the correspondent the sequence. So this is an element. This is an element of this space, L2 space, Hilbert space. This is a Hilbert space, of sequences, indices of complex numbers with this scalar product. And well, which is indexed by these numbers. So this is, we have a Fourier transform as usual. The only difference with, so to say, standard quantum mechanical picture, that we have a series rather than integrals. We have series rather than integrals. The Hilbert space of time-dependent automata wave functions can be expressed in a well, a little bit more complicated way. We call n finite affine automata plot equivalent if the limit plots coincide. So we deal with so they are links of the same number of torus windings having the common slope. So the picture which they produced on the torus are the same. This means plot equivalence for affine automata. Now we split all the affine subautomata of a subautomaton by this equivalence relation, and to every class of equivalence, it is uniquely defined. It is uniquely defined by this function, so to say, by this torus winding, and it is a countable union of balls of non-zero radii. Thus, to this ball it corresponds a probability. So again we have a function like this. Again we have a function like this. So this is how this type of function, these are series. This is a well-defined function of two arguments. This is real, this is integer, and this is a complex number. And it is a well-defined complex number because for every rho and k, the series converges absolutely. The series converges absolutely. But look here, what does this mean? What does this mean? What does mean this multiplication? If we take B, represented in Piatic, in base P expansion, and multiply by pk, and take 2p, this means that we take a shift of this number of its base P representation to higher order bits. But if we multiply by 2p this and take this one, this means that we will take an integer part, an integer part of this. This is just a shift. Okay, remember this. But now I will play a trick. I will play a trick. I will rewrite this term using another representation. You may use not only base P representation. You can use to represent numbers. You can use a representation with non-integer bases, and there are so-called beta representations, and where beta is non-integer, a real number, but non-integer. And I will take beta equal 1 plus tau, whereas tau is small, where tau is very small but not zero. Then this term is approximately this term, right? Because tau is very small, and thus we obtain this one. So instead of, but now t now is real, is now real number, we can assert it as real number. Okay, thus we come to this function. Thus we came to this function. It looks like a wave function of a free particle, because this is frequency, this is phase. This is phase shift. Well, let's say I like a free particle. But now note that if we have this picture, that actually we deal with binary world, because if we represent in this base, in this base, then necessarily the digits of our representation will be 0 and 1. This is not two-adic integers. They are still beta representation, but the digits will be only 0 and 1. Now we in this manner we obtain a function which is looking like t is real, right? Rho is real, so it looks at least like these are probabilities of obtaining these wave, so to say. So this is a composition of waves of different probabilities, and these are again they can be considered as elements of Hilbert spaces of these form spaces. These series rather than integrals, these series are because these are only countable number of indices. So these are again Hilbert spaces of sequences, and we actually have two types of we have constructed two types of wave functions by using Automata. I call this one coarse and this one fine, because this corresponds to Automaton, and here we played a trick. We changed, we replaced this thing by its approximate expression by using beta expansions like instead of base P expansions. So these are what we have come to. These are these things. Okay, so before measurement, Automaton is always in initial state. Then, an observer feeds an automaton with a long word, obtain, after a single measurement, the wave function collapses, so it reaches a minimal automaton, and we obtain a sort of interference fringes. This looks like that. Like, actually, how this look like? For example, this is a cyclic time evolution of a system. If there is no impact on the system, so this means that we send only zeros to our system, then it circulates. It's in a mixed so to say, in a mixed state. But if we send only a single one, depending where the state is, it will go here, or it will go here, or it will go here or here. If infinite time evolution, it means it's like that. So many systems, minimal automata are glued to this so to say general line, and thus we obtain when observing this, we will see the interference picture. And for example, we can calculate probabilities. For example, for this system, which just have seen, these are probabilities. It's easy to calculate. So with probability 1/6, we will get a wave which frequency is 5, 1/6 which frequency is 3, 1/3 is two-level ground state, so to say, which correspond to this function, and 1/3 for probability 1, for frequency 1, and these are okay. I have 5 minutes rest. I'm finishing. I need to finish. So these are the wave function which we already discussed. And it's two minimal subautomata. I have shown you the corresponding graph. Now I only want to finish with one thing, which can be also of interest. In this model, the time the collapse takes is not momentary. So the process of collapse is not instantaneous. It takes some time because the automaton need to run along the path which leads to a minimal leads to a minimal subautomaton. So it can be asked, what is this time? We can estimate this time. We can estimate this time by using the entropy. Again, we have this automaton which has subautomata which correspond to these affine functions, and this a probability to enter the so to say the minimal automaton having that affine function ax plus b, and this is the usual definition of entropy. The usual definition of entropy. So we have an automaton which has this fine automaton wave function, and the automaton has this entropy. Okay, but we already know that prefixes of lengths of paths which reach minimal automata, they constitute a prefix code. They constitute a prefix code. I stressed it at the very beginning. But having a prefix code, we can estimate the lengths, the expected code word lengths of the code. But expected code word lengths means the quantity, that it means time, because time is one step. So the length is how long is the path, the average at average. So means how many Planck time, so to say, passes before the automaton reaches its minimal subautomaton. And this is the estimation. This is the estimation which actually well-known inequality from information theory, which reads that the estimated code word length is not less than entropy, than the entropy. But on the other side, there are codes which are very close to the entropy, that they prefix code that constitute this inequality. But having a prefix code, we can construct an automaton with given distribution. This is an idea. So we can assume that from these two inequalities, that the expectation length means the time of collapse, the expected duration of collapse is about the logarithm of the number of states, roughly the same. Okay, this is what I am going to finish. I'm going to finish, but I want to stress some important things. The considered physical models, well, to what extent they could be considered as physical, this is another question. But what are important? They are purely information theoretic. They are more about how an observer processes the observational data rather than he performs measurements to acquire the data. I recall an it from bit concept of the well-known physicist John Archibald Wheeler. This is a quotation from his paper, a well-known paper also. And he wrote that the last analysis, it from posing yes/no questions. Recall, we finally had binary representation, right? And the registering of equipment evoked response. In short, all things physical are information theoretic in origin, and this is a participatory universe. This is exactly what we came to. This is exactly what we came to, and I'm finishing with you. The choice of metric which the data processed is crucial. Data may look completely random or completely non-random, depending on the choice of metric. The models assume that there are smallest indivisible temporal interval, the time units. The indivisibility means that events which happen within some temporal interval, the time unit, are considered as simultaneous. The processes, it's also assumption, are causal. Future has no effect on the past and present, but depends on past and on the present. It's like films. The sequences of discrete frames which are looking to a macroscopic Archimedean observer as continuous. And despite the models are information theoretic, we formally derived some things as Born rule. I haven't spoke about this, the collapse of wave function, and many other. And last but not least, the models can be applied to other areas. For instance, the mentioned temporal units can be applied to like units in physics onto some other units. But in application to digital economy, the units may be conventional units like days, minutes, etc. And smart contract, for example, is an automaton. It's also well known. So the time of collapse of automaton wave function is the time, the average time the contract is completed. Such unusual application of what have said. Thank you for your attention. My lecture and my mini course is over. Comments, questions are welcome. Thank you.
Thank you, Professor Nashin. Thank you very much. If there is any question or comment.
Vladimir, could you please comment? Can you hear me?
Yes, there is a question. Questions about limit plots. You showed a few explicit examples taking P2, but how different it would like if we took a different prime P. The same. It does not depend on P. It is for P2 because if it is shorter, so to say, to the calculations are faster. Nothing different. They will be windings of a torus. They will be all windings of a torus if we speak about affine plots. But maybe escape. Well, okay. How they can look like? Well, I can show you one picture. Look here. This is how the limit plot may look like. So you see, this is real. The picture is getting more and more condensed, and the limit plot is there. The limit plot will be that lines, but that lines. So this is how they look like. This does not depend on P, absolutely. The P may be prime, may be composite. It depends. Of course, if you take automata with different functions, you will obtain different plots. But the nature of a picture is the same. If I answer the question, this is another question. Okay. So okay. So you're satisfied, I see that. Okay. Are there other questions?
Yes, Vladimir, could you please comment about the Heisenberg uncertainty principle? I'm wondering about the way that this principle takes in the framework that you have introduced.
Yeah. Yes, I didn't talk about lengths, about momenta, about other things, but I talk about only one physical thing, which means time and actually the only physical parameter I mentioned. But I mentioned frequency. And I mentioned phase. If you look at this picture, if you look at this wave function, if you look at this wave function, and if you compare this wave function with of wave function of a free particle, that you can see that this is energy. This stands for energy. So we can introduce, I didn't do it, but we can introduce the entropy of energy. The entropy of time, which I already introduced, this automaton entropy, and the entropy of the energy. And I can show that the relations, the uncertainty relations hold, but in forms of, in entropic forms. There are papers, numerous papers of entropic relations, uncertainty relations, which, for example, Bilanitsky-Berulev, Polish mathematician, did a lot in this area. Well, there are many other papers, many other people, but it can be shown formally that uncertainty relations hold in this model as well, but in a form of entropic uncertainty relations, which means that the sum of both entropies, time, and energy is never zero. It is greater than something. Because there were no in this model, actually the Planck constant is one, right? We can assume that this is just one, and Planck time is Planck unit is one. So what I can show at the moment that the entropic uncertainty relations holds, and they does not depend on observation. They hold independently whether you make observation at Planck scale or at macro scale. They just hold in entropic form, in the form of the sum of two entropies is not zero. It's bigger than zero. This is the answer. If it is.
Thank you, Vladimir. Are there more questions? Okay, Vladimir, on the behalf of the organizing committee, I want to thank you for your participation in the conference. Thank you very much. I wish you luck, and I hope that we can see in the near future. Thank you.
Okay, thank you for inviting me, because it was very nice for me to give a talk here and to hear all the reactions, etc., in the discussion. Thank you. Bye. Hope to see you in the nearest future as well.
Okay, now we have a break. 10 minutes break? No, 30 minutes break. No. Okay, guys, we have vamos a comenzar. Hola, Edwin, ¿me estás escuchando?
Sí,
Edwin, ¿me estás
Sí, sí, sí.
escuchando?
Sí,
¿Estás
sí, ¿me
como
escuchan?
co-host? Sí,
Sí.
¿estás como co-host?
sí,
Entonces, si quieres, ¿quieres ser chairman?
vale.
Well, please. Okay. We got a chairman. Okay. Go ahead, Edwin. You are the boss.
Okay. Welcome everyone to this session of the Cimpa school. So, sorry about that. So for today's talk, we have the third session of the course by Chris and Claire about Piatic electrostatics. So thanks, Chris, for the wonderful course, and go ahead.
Great, thank you. Thank you very much. It's good to see everybody again this morning. I want to start, let me share my screen real quick and I'll talk through, all right, screen sharing. All right, so today, finally we get to the Piatic electrostatics. Yesterday was a lot of background, which hopefully sets us up to understand some of the results here. So I'm going to talk a little bit about the background of the problem. I'm going to talk about the Piatic canonical ensemble. Remember, that's a situation where we have a fixed number of particles. I'm going to give a quadratic recurrence for the partition function in the canonical ensemble. And then we're going to talk about the Piatic grand canonical ensemble. Right? This is the situation where the number of particles can now vary. So the energy and the number of particles can vary. We're going to talk about a particular tool on formal power series, which helps us compute probabilities. And then finally, the main result is a method to compute probabilities of cylinder sets. So I'm going to talk about how that works and give an example. All right. Background. So just to remind you of where we are, is we have an energy functional. This energy functional is modeled after the two-dimensional electrostatic energy functional, and that is to say that the energy of a system consisting of n particles is given by the sum of the pairwise energies of the particles, where each pair contributes minus log of the Piatic distance between those two particles. Right, so this is the potential energy, and this is basically just saying that these are charged particles and that they want to repel from each other. Right, so as we move these particles closer together, their energy gets larger and larger. Right, as we move these particles farther apart, their energy goes down. So the kinds of probabilities that we're going to be interested in are basically probabilities around counts of numbers of particles. The idea here is that our particles are indistinguishable. They don't have labels, they don't have identifiers. So really all we can talk about is the position of a particle, but not the position of a particular particle, right? So the information that that we have is going to be encoded in what's called a cylinder set or a cylinder sigma algebra. And the cylinder set is just a set where we identify some number of balls B, right? And some number of non-negative vectors. Sometimes we call these occupation vectors. And then the event that I'm denoting in capital B equals N is just the intersection of all the events where the mth ball contains N sub M particles, right? So this is basically saying I have some number of balls in the Piatics, and then I have some number of counts for each one of those balls, and I want to compute the probability that I see a configuration with the appropriate counts in the appropriate balls. So if there's only finitely many balls, and that is the situation we will be dealing with today, though the method is more generally applicable, we're going to be talking about the situation where we only have a finite number of balls and a finite number of occupation numbers for those balls. And we call those basic or simple cylinder sets because of the finiteness. And then we can generate a sigma algebra based on these basic cylinder sets, and that's called the cylinder sigma algebra. And it contains all of the information of all of the possible sets that we would be able to ascribe probabilities to if we're only given information about counts of these sets in particular, counts of particles in particular subsets. All right, so let me show you a couple of pictures. So let me start with this picture down here. This is the 5 adic numbers. I put 100 particles into it. And in this situation, these are just 100 IID, so identically distributed, independent, uniform random variables. So basically, I just picked a random point in the Piatics 100 times, and I wrote all of these points down, right? Because these are IID and random, there's no really repulsion between these things. If we think of them as particles, they would be neutral particles. And so there's nothing keeping them from getting close, right? We can also think of this as a thermodynamic model, but where the temperature is infinite. So the beta equals 0 situation. Remember, beta is this parameter, which is essentially 1 over the temperature. So when beta equals 0, we're at infinite temperature. At infinite temperature, even if the particles are charged, there's so much thermal energy that it far overwhelms the repulsion that they feel between each other, because there's just so much other energy in the system that and so essentially the charge becomes unimportant. So one way to think of this is also to think of this as being 100 charged particles at beta equals 0. All right, now let me go to this one right here, because this is 100 charged particles at beta equals 1, right? So it turns out it's not so easy necessarily to sample from this particular ensemble, or at least I haven't really thought a whole lot about sampling for various values of beta, besides beta equals 0, beta equals infinity. But beta equals 1 is another special case. And the reason for that is essentially, if you look at a random polynomial with p-adic integer coefficients, and if that polynomial happens to have all of its roots in ZP, most polynomials don't do this, but if you find one that has all of its roots in ZP, then it turns out that the roots of a random p-adic polynomial with all roots in ZP act like charged particles when beta equals 1, right? So there is actually a way to sample beta equals 1 by looking at polynomials with, in this case, I just chose integer coefficients, but look at polynomials with p-adic integer coefficients and then find one generated randomly, which splits completely in the p-adics, and then you'll be able to plot beta equals 1. So that's another place that we can sample for kind of another different reason. At any rate, when we look at the particles in beta equals 1, we see a much different picture than when we look down here at beta equals 0. When beta equals 0, for instance, right, we see 3 particles that are relatively close to each other right here. or a couple particles that are relatively close to each other right here. When we move up to beta equals 1, right? I mean, occasionally you see some particles that are kind of close, but really for the most part, the charges are trying to minimize the number of particles per ball, right? So especially once you get down to the smaller balls, it's trying to minimize the possibility that you have two particles in the same small ball. Right. So this is an example of, you can think of them as electrons on the Piatics if you want. All right. Okay, so let's dive in. That's kind of the background. Where am I going? There we go. Okay. So remember that in two-dimensional electrostatics, which we talked about last time, the joint density of particles is given by this Boltzmann factor. Essentially, it's the exponentiated energy times the temperature in there. There's a minus sign too, but it's essentially exponentiated energy. And when we exponentiate the sum of logs of differences, Piatic differences between particles, that of course turns into a product, right? And so we get a probability distribution like this, right? Basically, again, we have the van der Moon determinant. Here, I'm using absolute value. We are completely in the Piatics today. No other absolute values exist for our purposes. And so this absolute value here is a Piatic absolute value, right? And I'm integrating over the n-fold copy of the Piatics, right, of this van der Moon determinant type term, absolute value raised to the beta, right? This is the partition function. And the partition function is the denominator, which normalizes the probability density. Right? It's more than just the denominator. Most of what we're going to be talking about today is methods for evaluating the partition function. And the reason for that is because the partition function gives you tools oftentimes to actually calculate the probabilities that you want. And that is the case here. All right. Some people say that, you know, once you kind of establish a formula for the partition function, this is the first step towards solvability of the ensemble. The word solvability means a lot of different things in a lot of different areas of mathematics, but oftentimes when you're working in thermodynamics or mathematical statistical physics or whatnot, having some sort of closed form for the partition function is actually really important because it allows you to derive other thermodynamic quantities from it, and having a closed form might actually get you answers as opposed to just theorems, as it were. All right, so my first theorem is a recurrence, a somewhat complicated looking recurrence, but we'll see through the proof that's kind of natural after you digest it. But the idea here is that we're starting with the canonical partition function, so that integral over the van der Moon determinant to the beta, right, where we have n particles. That's the left-hand side. There's an n factorial there. We talked a little bit about that last time. Turns out it's just convenient to normalize, in this case, the n factorial on the left. And then we're going to find that the nth partition function can be expressed in terms of a product of other partition functions with these lowercase n's. And basically, there is one of these partition functions for each coset. So that should be a p minus 1, not a j minus 1. So j equals 0 to p minus 1. Those are the cosets. And then this is basically a sum of non-negative integers adding up to n. Right. So now you might say, well, this doesn't really look like a recursion to me because it is possible that Z capital N shows up on the right-hand side. And you are correct. Z capital N can show up on the right-hand side. However, it shows up with a different coefficient, right? It has this p to the minus beta n choose 2 minus n. And so you would be able to move that to the other side of the equation. And if you wanted to, you could write a pure recursion for Z capital N in terms of Z lowercase n's, where these are all strictly less than capital N. So this sum is over all vectors, right? That's almost the same vectors here, except we eliminate the possibility that one of the lowercase n's is capital N and the rest are 0. Right? We've essentially moved those terms to the other side, which introduces this term right here. So this gives a pure recursion for the partition function. If you, I should also say that in order to have a useful recursion, we also need to have some sort of base cases, right, or terminating cases where we know when to stop. And it turns out that the right answer there is the partition function with 0 particles is 1. The partition function with 1 particle again is 1. And the reason is essentially all of the energy coming into the system comes from pairs of particles. So if I just throw 0 or 1 particle into the system, there's no additional energy. And so you're just integrating over ZP to the n with respect to a probability measure, and you just get 1 out, right? So we have, this does give a recursion because Z0 and Z1 are both equal to 1. So the idea here, and really there's only 2 clever ideas in this entire talk. Well, other than things that smart people in the past did that aren't me, there's only really 2 clever ideas in this talk. And this idea isn't really all that clever. When you're in the Piatics, you have the strong triangle inequality, right? And having the strong triangle inequality is strong. Whenever you can use it, you should use it. And so essentially, I'm just going to be using properties of the Piatic absolute value in order to establish a theorem, which I think on the surface looks fairly deep. But once you understand that it's just coming from the strong triangle inequality, it feels less deep all of a sudden. Okay, but at any rate, there's something called the additivity of energy over cosets, or at least that's what I call it. And the idea is this, it's very easy, is that if I have 2 different particles and they are in 2 different cosets of PZP. Remember, ZP has this maximal ideal, right? And then it has a total of P cosets, if you include the maximal ideal as one of those cosets. And so I'm assuming I have particles in different cosets. And then what I'm claiming is that the energy contributed by those 2 particles in this case is actually 0. Right. And this is not hard to see. It's because if you have 2 particles in different cosets, the Piatic absolute value is equal to 1. And then the log of 1 is equal to 0. And so you're not contributing any energy there. So that is the central observation. So what we're going to do is we're going to, if I have lowercase x is, say, the location of my particles, and capital X is the random variables representing the locations. So usually this goes into the density function, and this is we're thinking about the random variables. But what I can do is I can relabel those random variables or that coordinate based on which coset the coordinates are in. So for instance, I can take this thing right here and say, oh, well, which ones of these particles are in the jth coset, right? And then I just make a vector out of that in the jth coset, right? So this is the particle location associated random variable in the coset J plus PZP. Okay. Now, one thing to notice about this is where the sum n0 plus n1 plus np minus 1 equals n. If I have a total of n particles, each particle has to land in some coset, right? And so when I've collected these up, I've basically n0 is the number of particles in the maximal ideal itself. N1 is the number of particles in 1 plus the maximal ideal, et cetera, et cetera. And all those have to add up to n. Okay. Now, in general, this vector x and this new reordered vector is not identical, right? Unless somehow this vector came already ordered. They differ by a permutation, right? But that doesn't matter. We've already seen that our particles are indistinguishable, and therefore changing things by a permutation doesn't change the state of the system. Right. So, I can either just think of this as being a vector of n points in ZP, or I can think of it as being kind of this multi-vector type thing where I have some number of particles in the 0th coset, some number in the 1st coset, etc. But both of these things refer to the same state of the system. Whether I talk about it in one way or the other, it's the same state. In general, once I have ordered my coordinates by coset, then there's going to be lots of different vectors x which correspond to that ordered coset, and that number is the multinomial coefficient with n in the numerator and all the little n's in the denominator, because essentially what you're doing is you're taking that tuple n and you're figuring out which spots are going to get the things for the 0 coset, which spot is going to get the things for the 1st coset, etc. Okay. All right, well, okay, the additivity of energy of a cosets, then, this is where the name comes from, is that the total energy of the system consisting of x particles is the energy of the system in the 0th coset plus the energy of the system in the 1st coset, etc., until we get to the p minus 1st coset, right? And this is, again, because particles in different cosets don't interact. So the only interaction energy we get in the system comes from multiple particles in the same coset. All right, so that's where the name comes from. Well, you know, the Boltzmann factor is just the exponential of the energy, so it turns multiplicative under this operation. So remember, the Boltzmann factor was the van der Moon determinant to the p-adic absolute value raised to the beta. But what I can do is essentially factor that over the cosets, right? I know that if two things are in different cosets, I just get a 1 there. So this product is secretly a product over p things, each one of those being its own absolute p-adic van der Moon raised to the beta power. Right? So this makes it look like that life is a little bit more complicated. I have introduced complications. Instead of talking about something simple, I'm talking about something more complicated. However, this setting right here, remember, this is an integrand. This is something that's in the integral for the partition function. And so this thing right now is set up for Fubini's theorem. And there's another theorem about Fubini's theorem. Maybe it's a meta theorem. But this is my meta theorem about Fubini's theorem. Fubini's theorem is the best theorem. Right? Anytime you run into either a couple sums or a couple integrals and you don't know what to do, you should exchange them if you can. Right? So Fubini's theorem is simple but brilliant. All right, so let's look at this. All I'm really going to do here is I'm going to substitute in for the integrand. Right? And then I have this factor right here, because when I was integrating before, I was integrating over multiple different states. And this is the factor that kind of takes care of the combinatorics. Except for that, now, I am able now to move this product outside of the integral. That is Fubini's theorem, right? So, of course, in order to use Fubini's theorem, one has to make sure that the integral is integrable. And so I'm assuming here that we have a value of beta so that that integral is finite, right? Is because it's already an absolute value, in which case Fubini's theorem we can use. All right. So now we're going to manipulate this a little bit. Right now what we have is our partition function expressed in terms of an integral over a coset of a very similar looking integrand, right? We're starting to see how our partition function might be expressible in terms of partition functions for smaller neighborhoods, because except for the neighborhood right here, this thing right here very much looks like a canonical partition function, just for a different value of nj. Right? If I was just integrating over zp, it would be another one. Right? So what I want to do now is I'm going to introduce a new measure. It's not really a new measure. It's the same Haar measure we had before, but I just want to restrict it to the maximal ideal. Really, this is just to give me, this is for notational convenience. It's exactly the same measure as before, but I just want to say lambda 1 is what happens when you take the measure that you had before and just apply it to the maximal ideal, EVP. Right. All right. So when you do this, a couple things to note, right, is that if you're in PZP, so if you're in that neighborhood, right, so if I have a point in the neighborhood, well, then there is some point in Y such that the point in the neighborhood is equal to P times Y, right? In other words, the way that you get the maximal ideal is take everything in ZP and multiply it by P. So if you have something in the maximal ideal, it was multiplied by P, right? So that says that there's something like that, right? This is useful, right? Because now we have a map from ZP to PZP, and we have an integral that we want to do, and we can essentially use U substitution, right? I mean, the integrals, I mean, maybe when I say U substitution, it is the same idea behind U substitution. I'm going to make the substitution X equals P times Y. Certainly, when I multiply X equals P times Y in the integrand, right, for each term in the integrand, I will get a absolute value of P that comes out front. If everything is multiplied by P, there will be a P there. So I will have an absolute value of P to the beta, and then I will have NJ choose 2 of those terms, right? So we know what happens to the integrand under the substitution. We need to figure out what happens to the measure. But it turns out, because lambda 1 and lambda are both Haar measure, even though additive Haar measure is not really designed to work with multiplication, it still does. And it turns out that if you look at the Haar measure of P times your variable, then that's going to be the Piatic absolute value of P times the Haar measure of just the variable. This is a more general fact. You can replace this P right here with any number, and it would go in right there. Okay. So what does this mean? This means that when I do my substitution, I get a P to the minus beta n choose 2 from this term right here. Right. And I get a P to the minus n from this term right here. So there's the P to the minus beta n choose 2 minus n. This in factorial, well, it's there, it doesn't matter. But the lemma is that if I'm looking at the partition function where I'm just integrating over the maximal ideal, that this is a power of P times the partition function where I'm integrating over all of ZP. And really what we're using here is just the self-similarity, right? The fact that the Piatics are a fractal means that the neighborhood PZP looks just like the big thing, it's just on a different scale, right? And all we've done is rescaled that neighborhood and said, oh, I can turn that integral over that neighborhood into an integral over the entire ZP. And that's what we've done. All right, we're getting close, but now if you remember, right, we were able to, once we partitioned our variables into the different cosets, we were able to integrate over the NJ-fold copy of that coset of an integrand that looks like the van der Monde determinant, the Piatic absolute van der Monde determinant. But now we can use the fact that Haar measure was designed for. Haar measure is translation invariant, right? And J plus PZP is just a translation of the maximal ideal. You're just adding J to every element in the maximal ideal, and that's taking you to this other coset. So if we look at the measure of J plus this vector, and what I mean by there is I'm adding J to every term in the vector, the translation doesn't change that measure, right? So I'm able to basically essentially get rid of the integration over the J plus, right? And just integrate over PZP, right? We also need to make sure that the integrand is translation invariant, right? But if I add J to both XN and XM, it's just going to cancel, right? And so I have translation invariant of the van der Monde determinant, right? Which allows me to say the following. If I want to integrate the van der Monde, the Piatic absolute van der Monde over the jth coset to the NJ, right? Well, I can also just integrate over the maximal ideal, right? I don't have to integrate over the coset. I can replace that integral over the maximal ideal, and it doesn't change the value of the integral. And again, the reason for this is kind of because the particles and the different cosets don't see each other. So if we don't think of them as cosets, if we don't think of them algebraically, just think of them as being kind of independent copies of the maximal ideal, right? I mean, they're not interacting, the particles aren't. So really you can think of those P cosets as being P copies of just the maximal ideal, right? Because they don't interact and the algebra is not coming into play right here. Okay. So we're putting all this together. What do we see, right? We had a sum over terms of a product with some betas out front of an integral that looked like this, right? This is just putting it all together. This integral is equal to the integral over lambda 1. The integral over lambda 1 is equal to the integral over lambda with this weird p to the minus beta n choose 2 minus n term. We're multiplying those all together, and then we're summing over all of the occupation vectors. And so this is a recursion. Now, I will say it's not the most friendly recursion to use necessarily. It is usable, of course. You can plug this into Mathematica and it will give you answers. But it's a little bit complicated because on the right-hand side, you have products of P different things, right? And that's fine when P equals 5, but when P equals 101 or some bigger prime, I don't know any off the top of my head, but I know there are some, right? That can be computationally expensive. So we'll come back and talk about a better recursion. But for now, this is the recursion that we have. Okay, let's talk about some probabilities. There's some simple probabilities that we can already compute, right? So in particular, if I am integrating the integrand over PZP to the n, then really that's just the event. I'm calculating the probability that all particles are in PZP. Right? So I'm calculating the probability that all particles are in PZP. And so I have an expression for the integral in the numerator. I have an expression for the integral in the denominator. Those things are only different by that weird term that showed up there, p to the minus beta n choose 2 minus n. And so that's the probability that all the particles are in PZP. Okay, this can be extended, right? The trick that we used right here is we essentially did U substitution. And so right here, this came from U substitution. Of course, I could make a different measure, which was a Lebesgue measure on a smaller ball, smaller than PZP, right? But then that would be all of ZP times a higher power of P. Right? In which case you would get a higher power of P here as well. But the argument largely goes through. If you are integrating over a smaller ball, you're just going to get a, if that ball has radius P to the R, you're going to get a P to the minus beta R n choose 2 minus NR, right? So the U substitution trick works. And what you find using the same trick is that if you want the probabilities that all particles are in a ball of radius b, then that's given by p to the minus r beta n choose 2 minus nr. Right. So some very basic probabilities come out almost immediately, right? And that's because partition functions of the kind I've given you, where I replace lambda with lambda 1, or maybe a Lebesgue measure on a smaller ball, essentially those are probabilities. Those are probabilities where you're demanding everything be constrained in that ball. Okay. There's another implication about the additivity of energy over cosets. And that's once we specify how many particles are in a ball, the distribution is independent of the locations of all of the other balls, right? So once I tell you, oh, there's 5 particles in the maximal ideal, it doesn't matter how many particles are in any other ideal or where they are, the distribution in that ideal is independent of everything that happens out of there. And that's just because the particles that are in different cosets can't see each other. So there's no way that the location of a particle over here can influence what's going on over here, right? So what this is saying is really the only dependence between particles. Oh, no, I don't want to say it like that. The dependence between particles depends on the number of particles in each coset. I'll try to make that clearer when we get to the canonical ensemble, because when we get to the canonical ensemble, we have a variable number of particles, and we get a kind of new kind of independence that we don't get in the canonical case. Because, for instance, if I know that all the cosets besides one contain all of the particles, well, then I know that other coset contains 0 particles, right? So there is kind of a dependence there, but we'll talk about that more when we get to the grand canonical partition function. All right, quadratic recurrence is for the canonical partition function. So our recurrence before was a little bit complicated. It involved multiplying together a total of p different partition functions and then summing over a complicated combinatorial term. Not the most useful or friendly thing to type into a computer. And so what I'm going to give you here is a simpler quadratic recurrence, which basically says that, well, it's quadratic because every term only depends on 2 partition functions, right? And then now this sum is a sum with n elements. That is a much simpler sum than the previous sum that we saw, right? The terms that show up in here look somewhat similar to what they did before. Okay, but this gives us recurrence now, right? Again, with the initial conditions, z0 equals z1 equals 1. Oh, shoot. All right. So we're going to do something unusual here. This is the only other clever idea in the talk. What we're going to do is we're going to artificially insert another coset of PZP into ZP. Right. So we have these 5 cosets. I'm just going to grab another copy and I'm just going to kind of glue it in. And I'm just going to pretend that I have 6 cosets, right? I'm going to call this new object T. I'm going to call the new extra coset, it has to have a new name. I'm going to call it P. And then the rest of the cosets I can just label as usual. So I still have a PZP and a 1 plus PZP and a 2 plus PZP. I just have this extra one hanging off on the end. Now, by doing this, I have ruined a lot of things. T is not a ring. It's not really any type of algebraic object. That's a little bit of a lie because you can view it projectively. But from the viewpoint of what we're talking about right here, it's not really an algebraic object. However, it is still a well-defined measure space, right? All I've done is essentially glued in another neighborhood, and I know how to do measurement in that neighborhood, right? And so I can make a measure on this object right here by essentially just saying, oh, well, I just have another neighborhood. And so I'm going to make our measure slightly larger. Now, when I do that, the measure is no longer a probability measure, but we can renormalize, right? We've added 1 additional coset. So I've essentially added 1 over P more mass to the total picture. I can divide by the appropriate thing and get a new probability measure there. All right. Nothing really changes by adding the coset, except we have to keep track of how many particles fall into it. Okay, so let's let n sub script p, right? That is the number of particles in this new coset, right? And what I want to do is I want to compute the expected number of particles in this new coset, right? So that expectation is going to be an integral with respect to our new normalized Haar measure. Okay. Well, when you compute the expectation of a random variable, right, it is the sum over the values of that random variable times the probability that they take that value, right? So the event that there are n particles in the coset P consists of n tuples where we have little n coordinates in P and the rest of the coordinates are not in P. In this case, the rest of the coordinates not being in P means they are in our original copy of ZP before we glued in this coset. Okay. So, one has to kind of follow through and make sure that you put in the appropriate combinatorial term, a binomial coefficient for how you distribute those particles amongst the coordinates, but that's not hard. And then if we want to express this in terms of our original partition functions, then we need to renormalize, right? But the idea here, let's think it through. The expectation of the number of particles is going to be, here's our sum. This is going to be n. And then the probability of having that many particles is going to be, except for the combinatorial term, is going to come from an integral over that coset P, the new coset P, right, where you have n particles, and then you're also just going to have a regular partition function over all of ZP, where you have n minus n particles, right? So again, these partition functions also give you some simple probabilities, as we saw before, and so this is one way of seeing these simple probabilities. The denominator here is just the normalization, right? In order to make this a probability, I have to normalize by the appropriate partition function, right? In this case, that's the partition function with respect to this measure on this larger set with the extra coset. All right, but right, this sum right here essentially came from the expectation. Remember, it's the value times the probability, right? But we can just expand this object right here in exactly the same way. You get exactly the same sum, except you just don't have an n right there, right? I mean, essentially what this is saying is that if you were to divide this side on the other side, is that the sum of the probabilities equals 1. All right, that is just the law of total probability. So we can expand this partition function in exactly the same way. The only thing that's different is the little n there. All right, so, well, I have this expression right here. I can cross multiply, move this to the other side over here. I can expand that as such. Both sides have the same p plus 1 over p to the n. I can cancel that from both sides, and I get this expression right here. Okay. Now, we're starting to maybe see where the quadraticness comes from, right? We're starting to see the terms that show up in the recurrence. And now here's the clever thing. It's not hard or smart. It's just a thing, is that if you really wanted to compute the expected number of particles in this new coset, you don't have to do any work. All the cosets are equal, right? And so what that means is if I have a total of n particles, and if I have a total of p plus 1 cosets, then the expected number of particles in any one coset is n over p plus 1, right? I did a lot of work, right? If I wanted to compute this expectation, that was unnecessary. Of course, the theorem is a quadratic recurrence, not an expectation. So what I can do is replace this expectation with the number, and then I can put these on both sides of the same side of the equation, and then I get, here is the expectation minus n, and then the last thing that I have done is notice that this is an integral over lambda 1. This is an integral over a smaller coset, and so we have a term of p that pops out from the u substitution if we want to write that down as a partition function over all of ZP. All right. So I should say that there is another proof of this, and I'll tell you how it works. I'm not going to give you the different proof of this. There's another proof of this after we prove the grand canonical situation. But I like this proof right here because it somehow uses the thermodynamic intuition. Right, you're saying, oh, well, the number of particles must be, uniformly distributed amongst these cosets. This feels like a more physical proof to me than the proof that I will allude to here in a minute. That is just a formal proof. All right, well, one thing that you can see immediately is that z and beta lambda is a rational function in p to the minus beta with rational coefficients. And the reason for that is that the initial terms z0 and z1 are identically 1. And then everything else that shows up has a rational number in it and some p to the minus beta to some power. All right. So you quickly get that. Of course, this is well known. There are general theorems that would say that this is true, that this should be a rational function, p to the minus beta. Not shocking, but this is just a really quick way to see it once you have this quadratic recurrence. All right, so one can do some examples here. Like I said, Z0 is 1, Z1 is 1, Z2 is this thing, Z3 is this thing. Now, I put these into Mathematica, and then I told Mathematica to turn it into tech, which is why they're not simplified any further. I wasn't going to try to simplify that. I don't care that much about what these things are. The fact is that you can compute them if you need them, right? They are complicated rational functions in p to the minus beta. You're not, as far as I can see things, going to come up with a very simple equation which describes these. If somebody figures that out, please let me know. I would be very interested. I don't think that's going to happen. So I think you just get very complicated rational functions in p to the minus beta. And the best you can do is provide a recurrence that tells you how to compute them efficiently. All right. Here is a picture. These are, let me describe what this is. So if I have 20 particles, I am writing beta as sigma plus IT because number theorists are crazy, and that's what they use for the real and imaginary parts of complex numbers for reasons I can't explain. So the real part is sigma and the imaginary part is T. Then I'm just integrating with respect to Lebesgue measure. These are all of the poles. Now, this picture is tilted. Really, the horizontal axis right here is the y-axis. And this is the x-axis, so you should kind of think of this as being tumped over. This is the negative, the left half plane. But basically the area that's gray is the area where the integral converges, the betas for which the integral converges. One thing that's really interesting that you see from this is a priori, we assume that beta was greater than or equal to 0 because beta is a temperature, right? But it turns out that the integral doesn't care that beta is a temperature. It doesn't know that. And the integral actually converges down to the real part of S is minus 2 over n, right? In this case, minus 2 over 20 is minus 1 over 10. So actually, the integral says that you can make the temperature a little bit, the inverse temperature a little bit negative if you want. The poles near the domain of convergence, the abscissa of convergence are simple poles. As you march away from that, they get more complicated. So like this pole at -1 has, I don't know, order 10 or something. I try to draw more circles around them to indicate higher order, but it's a little bit hard to see in this picture. There's a bigger picture in the paper. All right, so these things are complicated, but clearly there's structure here, right? I mean, the location of these poles is rather beautiful. And we do know, we can say very explicitly where the real parts of the poles should be. And we can say something about what the imaginary parts of the poles should be. And we can also say that the poles are actually periodic, right? So there is a period. This is actually half of the period right here. No, this is half of the period right here. If you were to mirror it and then duplicate that every 2 pi over log q, you would get infinitely many poles. All right. And that's because it's a rational function in p to the minus beta. You're probably complaining, rational functions can't have infinitely many poles. You're right, but rational functions in p to the minus beta can. There's a periodicity that comes in. All right. All right. You know, so before starting the Piatic grand canonical ensemble, this is probably a good time to just take maybe a 5 or 10 minute break. I didn't give you one yesterday morning, and I feel bad about that. But I think instead of talking for another 10 minutes and then stopping in the middle of this section, maybe we'll take a break here and then we'll start afresh. All right, how about we come back at 10:55 my time? That's about 7 minutes. Enough time for people to go to the bathroom, get a coffee, or escape if they're terminally bored.
Yeah.
What about 12 a.m., Chris?
Okay, that's fine.
To
Yeah,
be generous. Be generous, please.
I will be generous. This is for yesterday.
But let me tell you, you need some extra minutes at the end. You can have some extra minutes. Okay, no problem. So
Okay.
see you at 12
I'll see you at 12.
a.m.
Thank you.
Okay, guys, you have 12 minutes. Right now.
Quiero ver la dualidad del grupo de yo le aplico la dualidad con igual ¿qué sería? O sea que hay una técnica para estudiar. La idea es poner entonces pondría aquí lo vas a poder ver. Pero es la manera de identificarlo. ZP lo va a son unidades, entonces son unidades. Entonces va a ser básicamente un simplificado o la forma 1 más TSP. Ahora bien, pero de las unidades, SFP y después te queda un grupo compacto, pero necesitamos el igual de sí, sí, y se llama y entonces ahí lo que va a hacer es un mapa exponencial. Ahí está el mapa exponencial. Está metido eso debe ser porque es básicamente es que hay un teorema de tipos de entonces él hay un teorema se define una exponencial cada conexión igual que Entonces, por eso esto va a ser básicamente directo. Entonces vas a decir eso, ya,
Porque la carta de plan de proyecto que ahí tienen caracteres no son todos. Entonces, lo que está funcionando es todo para ver un tipo de lectura de estructura que es un producto de científica vacía. Un bocadillo. Un bocadillo. No, lo voy a comer. Voy a hablar. Y yo creo que estamos en la cada 5, 6. Por eso quiero ir ahorita. Y ya, después de estar ahí. A las 7. A las 7. Claro. Bueno, nos vemos más tarde. Gracias. Sí, señor. Creo que siempre tengo para nueva salida. Yo conseguí empleo ahí. El profe a mí, pero yo empecé. Ahí en los documentos preparé el examen de calificación. Bueno, yo preparaba pero en realidad la preparamos.
Vamos a volver. Vamos después. Falta un minuto. Ya vamos a comenzar.
We are ready, Evan.
Okay, so we will resume with the course by Chris. Chris, thanks.
All right, thank you very much. So now we are going to move to the Piatic grand canonical ensemble. So remember the setup here is that now our ensemble is attached to a heat reservoir, maybe the rest of the universe, and a particle reservoir, so particles can come and go. We introduced a term last time called the chemical potential, which tells us how easily we can transfer particles from our system to the larger system. But we also introduced this parameter, the fugacity, T, which allows us to view the grand canonical partition function as a generating function for the canonical partition functions. You can still get physical information from this version of the grand canonical partition function. You just need to plug in T equals e to the beta chi, where beta is temperature and chi is the chemical potential.
So Chris, before we go, can I ask you something?
Of course.
So you were saying that the beta is the temperature, right?
Yes.
So it should be a real number, right? But
yes,
you were considering that beta can also take complex values. So what is the meaning of the complex number as a temperature?
That is a good question. I don't know that it's meaningful to think of it temperature as complex. However, one can recast the canonical partition function is also the Mellin transform of the distribution function of energies in the system. So if you look at the energies in the system and you make a distribution function for it, and then compute the Mellin transform of that, which is, if you're not familiar, it's a multiplicative version of the Fourier transform. But usually the auxiliary variable that you put into the Mellin transform you view as a complex variable. And so from that viewpoint, the location of the poles tells you something about the asymptotics of the distribution function of energies. So there is a view for which the complex numbers are important. But temperature really, if we're only think of this as temperature or inverse temperature, we should think of it as living on the line.
Yep. Okay, thank you.
Yep, you bet. Yeah, I mean, by the way, viewing this as a generating function and then viewing this as the distribution, the Mellin transform of the distribution function of energies actually turns this into a kind of a version of the Mellin transform where one of your variables is discrete and the other your variables is continuous. Yeah, so, but at any rate, yeah, thank you. That's a very good question. I started more as a mathematician than as a physicist, so I move into the complex numbers whenever I want. All right, so the first theorem we're going to show for the grand canonical partition function is a functional equation, which basically says that if you look at, both of these should have a t in it. I apologize. Anytime I have a zt, I mean grand canonical, and anytime I have a zn, I mean canonical. And so the theorem should be zt, the grand canonical partition function, equals the grand canonical partition function integrated over the maximal ideal raised to the pth power. All right, now physically, this theorem has a very simple explanation. The logarithm of the partition function is called the grand canonical potential. And it represents the expected potential energy contained in the system. And if I have non-interacting systems, the grand canonical partitions, if I just make a new system artificially by saying these systems are now a system, but they don't interact, then I expect the grand canonical potential to add. It's an energy of sorts. And so if I just put in non-interacting systems, I just get additive behavior. Okay, well, we do know that our system consists of really p different systems, one per coset, right? And these don't interact. And so that means that the grand canonical potential of the entire system must equal p times the grand canonical potential of one of the littler systems, PZP, right? And that is essentially just the log of this identity, if I had this identity correct with t's right there. All right, so there's a very simple physical explanation for this. Let me just show you the proof just real quick, maybe. Right, we start with the canonical partition function, right? We had this recursion. In order to get the grand canonical, we sum over t to the n and all of these things, the n factorial cancels. Of course, we can write t to the n as t to the n 0 times t to the n p minus 1, because all those little n's add up to capital N. That allows me to slide the t into here, right? But now notice something. I am summing over all non-negative integers that add up to n, and then I'm summing over all n. So really, I'm just summing over a bunch of non-negative integers, right? Basically, that additional sum frees up the restriction on that sum right there. And now this thing is just clearly just a pth power, right? I basically have the product of p different things, and those different things are all that, where there's a t right there. Right, so the proof is relatively straightforward. Yeah, but it's a nicer, more concise explanation or way of writing that down. All right, another way of saying this is because, again, remember this thing right here, we could express this in terms of the integral over all of lambda. And so I can actually rewrite this as the partition function, the grand canonical partition function, when I'm integrating over PZP, the smaller set. Well, it's equal to this series right here. And this term right here is just the thing that came from the U substitution, right? Basically, this is the U substitution term, and that's the only thing that changes. Okay. And so another way of writing down the pth power identity for the grand canonical partition function is just to say that this series over here, the generating function for the canonical partition function, is equal to this series over here raised to the pth power. All right. All right. Now, let's just do a little bit of some easy examples to see how our intuition works. All right. Beta is inverse temperature. When beta equals infinity, we are at absolute 0, and we expect the system to stay in the state with lowest energy. Now, a state with lowest energy, right, only happens when each coset contains at most one particle. As soon as I put two particles into the same coset, I get an energy of 1 over p. If I have at most one particle in each coset, I have energy 1, right? Or, well, the energy is minus that. So the way to minimize the energy in that case is to put 0 or 1 cosets, 0 or 1 particles in each coset. And when you do that, well, here's infinity for the temperature, but what you find is substituting that in, you can only put 0 or 1 particles into a coset if you have less than p particles, less than or equal to p particles. As soon as I have p plus 1 particles, I can't do this. So the sum just goes from n equals 0 to p. P choose n tells you where you're going to put the particles, and then t over p to the n is the probability. And so when you I mean, that's just a binomial sum. And so that you can quickly see that at absolute 0, the partition function is just 1 plus t over p to the p. Right? Now, one thing to say, though, is let's see what the pth power identity says, right? We also have this pth power identity. Let's see if we can't recover the pth power identity in this case. And the answer is yes, we can. If you are in a coset, right, then the only way to have minimal energy once you are in a coset is just to have 0 or 1 total particles in that entire coset, right? Well, if I have 0 particles, I get a 1 right there, right? And if I have 1 particle, I get a 1 right there. And really, this should say 1 plus t, but there is a t over p that comes from this minus n term right here, right? So that is the thing that gives us t over p. But what you see is that this thing right here to the pth power is indeed the entire partition function. So you can verify the pth power law very easily in this case, because the set of configurations you have to consider is just quite small, and you can just enumerate them. Another fun direction, let's go from 0 temperature to infinite temperature. All right, so at infinite temperature, this is beta equals 0. Then all of the integrands are identically equal to 1, right? Remember, our integrand had this power of beta in it. And so when beta equals 0, you just get 1, right? And so when you are integrating the canonical partition function in that case, you are integrating 1 with respect to a probability measure. So you get 1 out, right? And so all of the coefficients in the series are 1. And so the series is just e to the t, right? Whenever you have a generating function, which is e to the t, that usually means that things are as free as they can possibly be. And that is the case here. The particles are just randomly, this is infinite temperature, they're doing whatever they want. And so you get this expression right here. And then it's really trivial to verify in this case that e to the t equals e to the t over p to the p. Right? So the argument works for the integral over the smaller set as well. And so the pth power identity is obvious in this case. Those are the two easiest cases, right? Everything else, the coefficients that appear in front of t to the n are complicated functions, rational functions, and p to the minus beta. So in general, you don't expect to get nice formulas for this, except perhaps at some very nice values of beta. Okay, so let's talk about just some very basic probabilities. Let's now talk about the event all particles are in the maximal ideal. Well, in the grand canonical ensemble, because the set of states is a disjoint union, basically indexed by the number of particles, then if we want all particles in PZP, and we have n particles, then we would integrate over PZP to the n. Well, since we have a variable number of particles, we have to take a disjoint union over that. And so, right, z t beta lambda 1, that really is saying integrate over all of PZP. And so the probability that all the particles are in PZP is what happens when you integrate over PZP, and then this is just the normalization constant for the probability measure. Right. So if you have these two things, if you have zt beta lambda 1 and zt beta lambda, well, then you can solve for the probability here. More generally, given any Borel set B, I can do the same thing. I take the disjoint union over B to the n. This is going to be the event. All particles are in B. And then the probability that all particles are in B is what happens when you form the partition function, but integrate over this measure. This is the measure which is Lebesgue measure supported on the ball B. And then you divide by the normalization constant there. All right, so let's just do a quick example. Let's just suppose B is a ball of radius p to the minus r and zp. Then the probability that all of our particles are in B is given by this series right here, right? And this series should look quite familiar. We have this P to the minus, and there should be a beta there, minus R beta and choose 2 minus NR, right? You get that same term again, and you have the canonical partition function showing up on the right-hand side. All right, well, one thing that's kind of cool about this immediately is for gap probabilities. So the gap probability for a ball is just the probability that that ball contains no particles. Okay. So the pth power in the theorem came from our distribution of particles into p cosets of pzp. So if we distribute the particles into all but one coset, we would get a p minus 1 power instead, right? So basically, right, we have these p cosets, and I said, oh, look, they divide up, and this gives us the p power law. If I just ignored one of the cosets and says, oh, that coset's going to have 0 particles, I would get a p minus 1 power law, right? All the particles would have to go into those other things, right? And what this means is that the probability, if B is a coset of PZP, so if I have a big coset, then the probability that there are no particles there is just 1 over the partition function for PZP, right? Which I think is kind of amusing. It's not obvious that this should be the case, at least not to me. All right, let's talk about more general probabilities. If I have an event in the Borel subset for ZP to the N, so this would be kind of an event that I might care about in the canonical ensemble. If I have one of those for each N, then I can make this disjoint union. And then the probability of seeing that event is going to be, well, there's the normalization constant, but it's a series, and that series consists of our integral that we had before, except now we're just going to integrate with respect to, this notation is slightly different than before, but hopefully it's understandable. The integral that shows up in the partition function is going to be the integral over AN. All right, so basically an event in the grand canonical ensemble is just a bunch of events. What happens when I have 1 particle? What happens when I have 2? What happens when I have 3 particles, right, et cetera, et cetera. And then the way that you compute the probability is you compute each of those probabilities in the canonical case, and then you can use those as coefficients into this series, and this tells us the probability in the grand canonical case. Of course, in real life, you know, all these probabilities right now, they do depend on beta, they depend on T, or the chemical potential, if you want to write it that way. So they're not looking like numbers, but if you had a specific value of temperature and chemical potential, you would get literal numbers out of this thing. All right, so we have seen that a lot of the expressions that we care about in the grand canonical ensemble come out in terms of power series. Not surprising, because the partition function is a power series, and the partition function often, as is in this case, gives you a lot of information about various probabilities. So it's not surprising that we have to deal with these power series, but we do. Right, so we see power series that look kind of like this. So what I want to do is introduce a general thing that I call the Q transform. It's probably a terrible name, but if I start with a power series, at this point it can be formal or it could converge, I really don't care. But if I have a power series and an indeterminate, again, this could be a number, but I'm just thinking of it as a parameter, then I'm going to call the Q transform of alpha, this series, to be a new series. And the series is almost the same, except I'm going to insert an n choose 2 power of Q into the series. Right? This is, right, the reason for that is because I'm trying to do something to model this piece right here. And so the Q transform is the thing that does that. There's also a convolution operator. So a convolution operator is a kind of multiplication. In this case, the multiplication is going to be, if I have 2 series, right, and I star Q them together, I convolve them with this star Q operator, then this is going to be this series over here. Essentially, I have a Q to the NM that I insert. Right? I didn't write this over here as a pure power series, which is powers of T, but you could. And you get a more complicated expression for the coefficient, but this is certainly a power series. When Q equals 1, we've done nothing. The Q equals 1 transform is just the identity transform. The Q equals 1 convolution is regular multiplication. Okay. I claim that for any Q not equal to 0, that you can make CT a ring under plus and this convolution right here. In fact, well, you can do this more general. You can show it's an integral domain. Not hard to see, but I'll leave that to you. The hard part is actually associativity, as you might surprise. Commutativity is easy. Most of the things are easy, but associativity just requires a little work. It's not hard. It just requires a big piece of paper. All right. Then the proposition is if I have one of these transforms, TQ, and if I look at the transform of a product, alpha beta, right, then the transform of the product is the convolution of the transforms, right? That's why I call it a convolution and a transform, because it acts like convolution of a Mellin transform or a Fourier transform or something. And sometimes we say when this happens that the convolution linearizes the transform, which is a weird word, but I guess it makes sense if you think about linear as in the multiplicative sense. Another thing, so this is what happens if you apply the transform to a product. Another thing that you could do is iterate the transform, right? You could transform and then transform again. And it turns out very easy to see, trivial, that when you iterate the transform, you just change the Q. You bump up the power. All right. So, well, I don't want to do this for general Q. I want to do this for Q equals P to the minus R beta. Okay, because that is something that showed up with an n choose 2 in my series right here. And so I want to, I'm going to subscript that with an R. And here, this notation is a little bit ambiguous. Star R is going to be the convolution operator for this transform. That bumps up against this notation a little bit, but we're not going to use the transform or the convolution a whole lot. So, all right. So I can rewrite things, because if I just look at what this transform is doing, and if I remember what the P power law was saying, the P power law is now saying that Z of T beta lambda is equal to T1 of Z T over P beta lambda. That T over P right there, let's go back up here. That's taking care of the minus N, right? So here I'm dealing with T1, right? So I would just have a over P right there, right? So that's where that comes from. That's what takes care of the other additional thing that comes up, right? So we've taken care of the n choose 2, and then the n is taken care of by plugging in T over P. And more generally, right, if I have a Haar measure on this tiny little ball, P to the R ZP, then one can do the same thing. One can write the partition function over that tiny ball as being the rth transform of the partition function for all of ZP, but you have to plug in a T over P to the R into the fugacity variable. Right? And similarly, there's nothing too special. Our Pth power law says that we could take the partition function for ZP and write it in terms of a product for partition functions over the cosets. What if I start at a part for the partition function over a ball that's not ZP? That ball consists of 5 little balls inside of it, kind of the cosets inside of there by self-similarity. And so there's a similar Pth power law, right? Except if you are in a smaller set than all of ZP, instead of using ordinary multiplication, you have to use the star R. You have to use the rth convolution operator. But there still is a Pth power law that comes along. So for instance, one thing I could do is say I just want the original partition function. I know that I can write that as T1 to the Z of T over P with regular multiplication to the P. Remember, star 0 is just regular multiplication. Right? But then now, Z over T to the P beta lambda T1, right? That is actually a smaller set. That's the partition function of a smaller set. Anytime you hit something with T1, you're essentially saying, oh, I want to look at the same thing, but in a smaller set, right? So I can expand each one of those as their own pth power, right? So I express that as a pth power. It's going to be a star 1 pth power, right? Yeah. So, and T1 of T1 is T2, right? So you can move T2 in. So I have T2 of Z, TP, beta, lambda, star 1P, star 0 P. But T2Z is a Z over lambda 2, right? Integrated over the smaller ball where I had to plug in T over P again. And so if I wanted to, I could expand my pth power identity as far as I wanted, right? I could do this again by expanding that over an even smaller set. All right, so with these convolution operators and transforms, then we can do a lot of things, at least symbolically. All right, since probabilities are generally fractions where the numerator is a partition-like function thing and the denominator is a partition function, I am going to define, this is not really well defined, but I think you'll be okay with it. If you're given something like that, I'm going to define T to the R to be just acting on the numerator. A little bit not well defined, but generally speaking, these probabilities come where the numerator is handed to you and the denominator is just the partition function. So if I say TR applied to that fraction, I mean hit the numerator with it. And then my claim is that if I have an event A, okay, well, then I can make a new event by multiplying everything in that event by P to the R. This essentially kind of pushes it down, make a smaller fractal version of that event. But then the probability of that new event, this kind of contraction of A, is just the probability of A acted on by this Rth operator. Right. So if you can compute this probability right here, then you should be able to compute this probability right here, at least in terms of a formal sum. Okay. Now, we need to do one more thing. Well, we need to do a few more things, but one thing that we need to do is notice that if I'm given a coset, my favorite coset, each coset looks like a little version of ZP, right? So what I'm going to do is I'm going to define this pi, right? So if I have pi of a point in that coset, right, I am basically going to return just the x value. This is basically what happens if you took a coset and you just wanted to inflate it to all of PZP. Right? You say, I have this little event in this coset. I want to make an event on ZP. I can make an event on ZP by inflating that event, right? And so what this says is that if you have an event in that coset, right, then the probability of that event, right, can be written as the probability of the inflated event, right? So a probability in ZP, and then you push it with T1, which kind of pushes it back down. All right. Now, but we'll see why we want to do this. Right? We're getting to why we want to do this. Okay, cylinder sets. Okay, we're gonna be computing some probabilities of cylinder sets now. And the simplest cylinder set that we can possibly imagine is the cylinder set NZP equals N. Maybe that's the simplest one we can imagine. It's a pretty simple one. This is basically saying what is the probability that in the grand canonical ensemble you have exactly N particles. Well, that probability is pretty easy to compute because we know that the partition function in the canonical ensemble case, right, are the coefficients in the power series. So somehow that probability must be able to be rolled out from that coefficient in the power series. And the answer is yes. The nth coefficient in the power series is t to the n over n factorial times z in beta lambda, right? And we just need to divide by the normalizing constant. And this tells you the probability that you have exactly n particles. This makes sense, of course, because if you were to sum over all n, you would get 1 out. And that's the law of total probability. All right, so this is a particularly simple example, at least compact, let's say, because this term right here could still be quite complicated. All right. Okay, so here is the recursion for our cylinder sets. So like before, we had a bunch of balls, and we're saying for these balls, we're specifying a number of particles in each ball. We can relabel and reorder the balls so that we put all the balls in the 0th coset together into a vector B1. We take all of the balls in the first coset, we put those together. Basically, we're going to lump these together into various cosets, right? And so the jth coset, Bj, will be for the jth coset, and Nj is the occupation vector. What this says is the probability of having this, of seeing this particular cylinder set is equal to the product of the probabilities of seeing the cylinder sets in the individual cosets, right? And again, this is just because the cosets really can't see each other, right? The cosets really are kind of independent of each other because there's no interaction energy between particles in this set and particles in this set. And so if I want to compute the probability of a cylinder set, and my cylinder set is comprised of a bunch of balls, well, then I can just put all of the balls that are in the 0th coset and compute the probability of that cylinder set. Let's look at all the balls that are in the first coset, compute the probability of seeing that cylinder set, and then continue. So this is essentially comes from independence, right? This gives us a recursion for these probabilities. If we started with a simple cylinder set, well, that means that there would be only a finite number of balls in total, right? And so every time we can basically repeat this thing right here, and there's a recursion that allows us to terminate either when we are looking at the event, the total number of particles in the ball Zp equals n. We know how to do that, right? Or the other possibility, the other terminating condition is that we have specified nothing about any of the balls in a coset, right? Maybe I just say, oh, I'm interested in knowing what the probability that there are 3 particles in the second coset. That would leave an empty condition for the maximal ideal. And if you have an empty condition, that would be, right, the number of the empty set equals the empty set. That's all of omega. And so the probability of that case is just equal 1. All right. So as a corollary, right, maybe this is the more useful recursion, the probability of, once I organize my balls into cosets as such is equal to the product of the probabilities if I inflated each one of those things to all of Zp, computed its probability, and then pushed it down by T1, right? So let's do just an example. Here is a schematic of a cylinder set. Here I am in Z5. These numbers say I am interested in the probability that there are 2 particles in the maximal ideal, 0 particles in this neighborhood, 2 here, 5 here, 5 here, 4 in this little neighborhood, 6 here, 0, 1, 1, and 5 here. Now, I will say we can already tell that this is going to be a low probability event because at any reasonable temperature of beta, the particles kind of want to equally distribute, right? They're trying to get away from each other. So the probability, much less of any of this other stuff, the probability of having 5 particles in this little ball might be rather small, right? Much less the probability of 5 particles in this ball and 0 particles in this much larger ball. We're looking at a pretty small probability here. Nonetheless, perfectly reasonable cylinder set to consider. Okay. So what the corollary says is that I can compute the probability of the cylinder set by computing the probabilities of each one of these things, each one of these events viewed as an event on all of ZP, right? So that pi operator basically takes that neighborhood and makes it all of ZP. So I can view the probability of this cylinder set as the probability of this cylinder set, hit it with T1, times the probability of this cylinder set, this one right here, hit it with T1, times the probability of that one, hit it with T1, times the probability of that one, hit it with T1, times the probability of that one, hit it with T1. Right. So this is the recursion. It's saying that I am able to compute the probabilities of cylinder sets by looking at probabilities of cylinder sets and cosets, but there's going to be, those cylinder sets and cosets are going to be less complicated in general, right? You're going to have, in general, fewer balls in each coset than you have in total. So that allows the recursion to terminate. So now, well, let's look at these right here. First, the probability of having 2 sets in all of ZP is something we already computed. It is going to be t squared over 2 factorial, Z2 beta lambda, ZT beta lambda. I'm going to hit that with T1, right? When I hit it with T1, I get a P to the minus beta 2 choose 2. So that's just 1. And then I have to plug in T over P when I hit it with T1, right? So T1, that whole probability right there is just that number right there. Okay. Now that means, okay, substituting it in. Notice also, we said that the probability of an empty cylinder set, notice I'm not specifying anything about where particles should be in neighborhoods in here, is just 1. Right, so I can get rid of that term completely. And so here's the first term. I got rid of the last term. And now I just need to compute these. Well, let's look at P of this thing right here. Well, P of this thing right here, now I can use the recursion again and say that's going to be a T1 of this cylinder set, T1 of this cylinder set, T1 of this cylinder set, T1 of this cylinder set multiplied together. So here is the T1 of the cylinder set 5. Here's T1 of the cylinder set 5. Here is T1 for the cylinder set 2. And here is T1 for the cylinder set 0. Okay. If I look at the next neighborhood, so I've essentially computed the probability there, and then I can hit that with T1. If I look at this one here, this probability, well, I actually have to kind of use 2 recursive steps, because one of these is a coset, perfect. And so there is just the term for the coset for 6. But this thing right here is the coset of a coset, right? So I actually have to go down even further, right? I mean, and that basically is introducing some additional complexities. Notice, here's what it's introducing. This is T over P for the 6. This is T over P squared because it's even deeper. It's farther, it's a smaller ball. And also that P squared, that's like the P to the R. It changed the n choose 2 as well. All right, and then for this one right here, well, okay, again, notice we're gonna have to kind of recurse twice. So it's going to be T1 of P of having 1 particle in there, T1 of P of having 1 particle in there, T1 of P having 0 particles in there, right? So that's the first term. And then here I would have T1 of T1 of having 5 particles in there, but T1 of T1 is T2, right? And one can, at this point, anytime I am hitting something that's just a monomial with T1, a monomial is a particularly simple kind of power series, right? You can very explicitly just write down what T1 is. It's just going to have a power of beta to the minus n choose 2. And so it's very easy to do these calculations for T1 because everything that's showing up now is essentially just a monomial. All right, putting it all together, right? This looks like kind of a mess, but I simplified it a little bit. This is a little bit wrong because I forgot to write the p to the minus beta. I think it was 124. I forgot to include all of these 5 to the minus beta terms in this thing right here. I will say that most likely, I don't know your life very well, but for any reasonable value of t or beta, this might be the smallest number that you've ever seen in real life, right? This is a tiny number. This is a super tiny number, right? And that's even if you ignore the 5 to the minus 124 beta, right? So, and this is kind of reasonable, again, because we really do expect the particles in the grand canonical ensemble to well distribute. They're charged. And so you really shouldn't have a situation where you have like 5 particles in a little tiny ball and no particles in a really big ball. That's a really unlikely situation. And that's what we're seeing right here. All right, I got through that a little quicker than I thought. That is the end of what I had prepared, was just to kind of show you that you can actually use this for calculations. I will talk about just in the last, it won't even take 5 minutes, about how we might actually evaluate these numbers, right? I've told you we have computed the probability. Yay, we're done. Well, we've computed the probability up to these numbers right here, but the numerator is easy to compute in general because we have the quadratic recurrence, right? So especially for Z1, Z2, Z4, Z5, Z6, these are low values of n. That quadratic recurrence is not particularly expensive to compute. It can be memory intensive to store the rational functions, but it's not that difficult to compute. So those numerators are all achievable as explicit functions, exact explicit functions in terms of beta, right? So the numerator you can compute explicitly. The denominator, this is the grand canonical partition function to a high power, but I'm not worried about the high power. We saw 2 easy cases where we computed the grand canonical partition function: infinite temperature, 0 temperature, all right? But those are the kind of the uninteresting ones, kind of the endpoints of an interesting interpolation of temperatures. So if you wanted to use this to actually compute a probability, for instance, maybe you needed a calculation like this to build a bridge. Don't use this one to build a bridge. I'm sure there are mistakes, but maybe you need a calculation like this. What you can do is you can say, I want to know this probability up to some tolerance, up to some epsilon. And then once you figure out what that epsilon is, it's going to tell you how many terms you need in the grand canonical partition function to allow you to calculate the probability within that tolerance. And then the coefficients in the grand canonical partition functions are just canonical partition functions. So you can use the recursion in order to get those coefficients out to whatever degree is necessary. And then that gives you the ability to write down the probability to arbitrary precision, right? With the understanding that arbitrary precision means that, you know, you might have to run the recursion for a long time in order to get out to the appropriate tolerance for your probabilities. So all of this is kind of explicitly doable if there's any reason that you need to do it. So that is the end of my talk. I apologize for ending a little bit early, but maybe this is a good opportunity, gives people time to ask questions.
Thanks, Chris. I would like to ask everyone to give an applause to Chris. Thank you, Chris. Okay, so do you have any question, guys, for Chris?
Hello, Chris. I would like to ask you to comment about future research lines for inverse equations for the young audience and also for the non-young audience.
All right, so future directions for this?
Yes, please. Some basic ideas.
So here's one question that I've had for a long time, and I've posed it to several grad students, but nobody has nibbled on it yet. But one thing you can do is you can look at the occupation of, let's just sample. Let's say we do a sample of 100 particles in Z5. And then you know that kind of the lowest energy configuration is going to be when, how do I want to put this? If you look at two particles in Z5, there's a least common ancestor to them, right? Z5 or ZP is a tree. And so if I look at any two particles, there's a least common ancestor. And one question I have is, in general, what is the distribution of least common ancestors in ZP, right? And the reason I ask that is because in the low energy configuration, all the least common ancestors are at the top of, towards the middle of the picture, right? Everything, basically, the least common ancestors kind of condensed towards the middle of the picture. And so what you get when you look at the picture is towards the middle, how do I want to put this? You get a region in ZP which is completely filled, where every possible least common ancestor is a least common ancestor. And then you get a little region after that. I think of that as the solid phase, right? All the least common ancestors are packed as close as possible to zero. That's the lowest energy configuration. And then if you're at higher temperature, there's going to be some fluctuations from the lowest energy, which means that there might be some holes, some places where you would expect to see a least common ancestor, but you don't, right? And I call that the liquid phase. And then there's a phase afterwards where there are absolutely no least common ancestors, right? Where basically that you have packed that, and that's the gaseous phase. So one question I have is, in general, for the number of particles n, and maybe that should be a power of p or something, maybe it should, scale exponentially or geometrically as opposed to linearly. What can you say about the size, the depth, maybe of the liquid phase, of the solid phase and the liquid phase there? And is there any phase transition? Like in particular, we know that we can take beta a little bit negative, right? Is there a phase transition that happens in the least common ancestor process as you move the temperatures negative? That's one question I'm interested in. Another question that I'm interested in, and I talked about this a little bit previously, is you can view the Piatics as a tree, as a regular, the Piatic integers are just the regular 5-nary tree, right? There's a root, every node has 5 children, and you can make this large graph. Well, you can do this with other graphs as well. They don't have to be regular. And there is a way of introducing a measure on a tree like that, a rooted tree, which agrees very similar to the Haar measure that we constructed here, except it's not a Haar measure because we don't have a group. But you can set this up to kind of come up with a random version of this, of electrostatics on these trees that maybe are not regular. The question that I have comes back to number theory, right? So it turns out that, for instance, if you have a tree, and suppose every other generation has 2 children and every other generation has 5 children, right? So 2, 5, 2, 5, right? So this is kind of a homogeneous, but not regular tree, right? In that case, you can show that the partition function, the canonical partition function, is a rational function in 5 to the minus beta and 2 to the minus beta, right? The 2 children and the 5 children, you get kind of this generalization. It's not hard to see, but and then, so my question is there are lots of situations where you get trees where every single node splits uniformly randomly though, right? Maybe now a parent randomly has 2 children or 5 children, right? And so now this is not a homogeneous tree and not a regular tree. but is something that you can still do electrostatics on in expectation. Now, here's my question. That was just the setup. If you're in a number field, okay, so suppose you have a number field, and let's think it probably has to be bigger than Q. But no, let's just look at Q. If you have a number field over Q, then all of the primes in Q potentially split into primes upstairs, right? So the prime 2 may no longer be prime when you move to Q adjoin I or something. Okay, so now if you can make an infinite tower of field extensions, maybe an exhaustion of all the rational number or all of the algebraic numbers, but just some tower of fields. And if you make a tower of fields for every prime downstairs, you get a tree, right? Because every time you add a new field, you have a potential splitting. And Chebotarev density says that the splitting is not random, but is only one of a certain kind of types, right? There's only certain kinds of splitting types of primes. So what you get for this tower of fields is for every prime, you get a tree. And that tree, all of those trees have the same probability laws, right? Because, well, asymptotically, at least by Chebotarev density, all of the primes are kind of splitting randomly in the same way. So you get a way of having a huge number of trees with the same law, right, on which you can do experiments. And one question that I have is, what does the Piatic electrostatics tell you about the splitting of primes, right? Are there any conclusions you can draw from the electrostatics about the splitting of primes in these trees? Probably on average splitting of primes. You're not going to be able to talk about specific splitting of primes, but on average. So that's a very number theoretic result, but it's something that I have often asked myself. So.
Thank you very much. Any other question for Chris? So I have a couple of questions, Chris. There is one question on the chat.
Yeah, I am, but you may ask your question first, and then maybe if you want, I don't know. I have a question that, for example, if we compare the partition function with the complex case, then in the complex case, the partition function is a kind of trace, is a character of a representation of infinite symmetric group.
Okay. Yeah.
And then in the Piatic case, then is it the same? So I think here also you have the representation of the infinite symmetric group, and you can do the same thing. And I have one question more, that your partition function is a kind of entropy. Mm-hmm. Entropy of a measure on the space of partitions, yes. in the space of Young diagrams, or mm-hmm. kind of like that. Mm-hmm. And then I want to ask that if in the Piatic case, if you can tell some the same thing, or how you just an idea. I want, if you can. Thank you.
Yeah. No, this is excellent, and I don't know. I will say I don't know the answer to your questions already, but certainly I have thought a little bit about the representation theory, or kind of the theory of Schur functions around the van der Moon determinant, because they're generalizations of the van der Moon determinant that you can kind of play similar games with. In particular, you can do the multi-charge situation where you have a bunch of different kinds of charged particles, and then you have to use the confluent van der Moon determinant, which is just another similar thing. But I don't know the answer to your question as to what does this say in the Piatic case in terms of representation theory. On the other hand, the idea of looking at entropy is a good idea. It's not something I thought about, but it's something that I do know a little bit about. So I appreciate the idea, but I haven't thought about the implications in terms of entropy or ergodic theory.
Okay, thanks. So my questions are really basic. So what is the meaning of the poles? Because the canonical potentials are rational functions, right? So there appears on some poles on the denominators on beta. So what is the meaning of those guys?
Yeah, that's, well, the way I think about them. And you know, originally when I was starting this problem a long time ago, I was not viewing this in terms of electrostatics. I was just interested in the integral of the Piatic Vandermonde, just because that was kind of where I started. And so my initial, before I kind of understood what I was doing, my initial way of thinking about selling the problem would be, you know, what is the distribution of values of the Piatic Vandermonde, right? Just if you were to pick a point uniformly from ZP to the N, what would be the distribution of the Piatic Vandermonde? Then it turns out that the partition function is the Mellin transform of that distribution function. And so the poles, if using Mellin inversion, basically the location of the poles tells you certain asymptotic terms that show up in the asymptotic expansion. So for instance, I think it's the case of the terms closest to the imaginary axis. So the rightmost poles tell you something about the really small values of the Piatic Vandermonde. And I think as you move farther out, they're telling you about the larger values of the Piatic Vandermonde. But each pole will introduce a term in a series which in principle should tell you the asymptotics of the distribution of the Piatic Vandermonde, or equivalently, because the log of the Piatic Vandermonde is the energy, it gives you the distribution of energies. So that's how I think about the poles, but that's because I was raised as an analytic number theorist, and that's how we think about poles, is they, you know, you move the line over and they tell you an asymptotic term in some sort of expansion that would be otherwise unavailable. So that's how I think about them right now.
Thank you. Thank you. So the other question that I want to ask is, we saw that for the grand canonical partitions, we have the grand canonical potentials. Sorry, we had like two extreme cases. In one place, there was 1 over p or something like that, and on the other hand, there was some exponential function. So, in general, what type of functions do we have there? I mean, there are analytic functions. They are like a classifier, or they're easy to describe, or
you know,
I
don't know. In general, they're going to be, I would suspect, highly well, they're rational fun. No, they're not. They're going to be highly transcendental. It is conceivable that they're hypergeometric, but I doubt it, right? I mean, series which have rational functions as coefficients, special kinds come up in terms of hypergeometric functions. I can't imagine that that's true here, right? I don't think the degrees of these polynomials grow in the appropriate way to be like a 2f1 or something like that. And I don't know the answer to the question, mostly because I've really only computed the rational functions up to about 20. And they're long and they're horrible, and I can't even simplify the rational functions themselves, much less after I put them into a series. But I would love to find even any other value of beta for which there is a closed form. I would hope that beta equals 1 would have some sort of closed form, because it has this other very natural interpretation in terms of probability of splitting of polynomials. It feels like if there's going to be another value, that would be the one. It's also the value that's multiplicatively halfway between 0 and infinity, which kind of gives it a symmetry feel. That would be my hope, but I have no values of beta other than 0 and infinity for which I can say anything precise. I wish I could.
Okay. Thank you very much. Any other question for Chris? So,
Yeah, there are more
guys
questions.
in the room, do you have any other question? Okay, if that is not the case, so let's thank Chris again. Sorry, do you have?
Sorry, Ellie. Let me say something.
Yeah.
Can you hear me?
Yes.
Yeah.
On behalf of the organizing committee, I want to thank you for participating in the conference, Chris.
Thank you very much.
I
Yes.
hope we can see you in the near future somewhere. Thank you.
Thank you very much. Yeah, and I would love to see y'all in person sometime as well. Feel free to shoot me emails if people have questions or want to talk more. I love talking about math. So I'm happy to talk about math with anybody in the room at any time.
Okay. Okay, so let's thank Chris again. Let's take an applause. Another one. Thank you. So thank you again, Chris. So okay, we will continue at before the lunch. There is a lunch break, right? Yeah.
Yes. Just a reminder that we have the social event.
Okay, yeah. Don't forget, guys, that you're going to get for the guys that are in CIMAT, you're going to have the taquiza this night. So that is a very special arrangement of tacos. So that will be at 7, right? In Terrace 601. And there was another announcement. The talk of Professor Cole will be on Tuesday at 1, right?
1:30.
1:30. Okay. So any other comment? Okay. Okay.
Bye.
So, okay, thank you guys. Enjoy your lunch and see you.
Edwin, ¿me escucha?
Sí.
¿Va a estar después del almuerzo o ya es demasiado tarde para usted?
No, ya es demasiado, Wilson, lo siento.
Lo hago yo. Nos vemos. Bye bye.
Vale.
Eso sí, no sé porque eso es con el Cimpa, eso yo no lo controlo. Yo le aconsejo que le pregunte quién fue el correo. Pero es que él está en España, imagínense. Sí, pregunte, porque yo realmente no sé cómo hacer. No, pero ahora puede.
Hola Wilson, ¿me oye?
Hola Hugo, ¿me oyes?
Hola, sí,
Ah, perfecto. ¿Cómo estás?
bien, bien. No puedo
Oye,
poner
te
mi
iba-
cámara.
¿no la has puesto o te tengo que autorizar?
A lo mejor me tienes que autorizar.
No. ¿No?
¿No?
Tienes que, la cámara también la tienes apagada, ¿eh?
No, está prendida.
O tienes un fondo de pantalla.
Sí. Pero enciendo la cámara y
Ahí se ve algo. Tienes un fondo de pantalla. O estás compartiendo la pantalla.
esa no es mi.
Sí se ve ahí, pero muy temprano. Allá se ve, pero aquí yo no lo veo en la. Allá se ve, allá se. No sé si no.
Pero ahorita sí se ve.
No, bueno, allá donde está, se dice la luz, es la pantalla de Google.
Sí, sino que hubo un momento ahorita mientras estaban ahí esperando que apareció ya está la pantalla.
Compartir pantalla.
Sí, aunque mira. Hugo, creo que estás compartiendo la pantalla.
Ok, déjame.
Si quieres, cierre, a ver.
No, pero ese no es mi fondo de pantalla.
Ese no es un fondo de pantalla, porque aparece, no sé si lo estás viendo, aparece como un planeta con una estrella al fondo y dice como vean fis.simstar.m.
¿No será que me quedé con alguna? No.
O si no, salte y vuelve a entrar, Hugo, porque ya se está aproximando la.
Ok. Ok.
No, pero no soy yo, es él. No. ¿Quieres que la estar? No, está en Italia. Bueno, pues me conecto yo. Sí, por si acaso, sí. No, pues porque acá no tengo problemas, ¿eh? Si quieres explicar esto. Pues yo estoy, pero no todo. No, pero que me. Sí. Ahora me voy a conectar yo, me pones también de volver a. Sí, por si acaso hay algún problema, digamos un backup ahí. Sí. ¿Porque yo veo que Rogelio? No, Rogelio no, yo creo que sí. Eso me imaginaba.
No sé qué pasa.
Oye, sí, estás apareciendo de nuevo. Oye, a ver, ¿sí me escuchas?
Sí.
¿Sí me escuchas? Trata de compartir tu pantalla en la presentación.
Ok. Usar cámara, permitir.
Yo no tengo que ser co-host. No, es Israel. Sí, no, por favor, le permite que comparte la pantalla de sí. A Hugo, para que estemos seguros de cuidar.
¿Así se puede conectar varios? Sí, 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 sí. Por el otro lado. Bien.
Hola Hugo, ¿pudiste compartir la pantalla?
Permíteme, Wilson.
Ya apareció en la computadora, pero no te vemos. Solo aparece tu... Si quieres, coloca la presentación. Y ahorita, o si logramos que aparezca.
¿Se ve?
Sí, la presentación la estamos viendo, pero no te vemos, no te vemos la cara. Aparece lo que te decíamos, la Tierra y aparece el Sol en el fondo.
A ver. Cambiar imagen.
Profe, él tiene dos pantallas.
¿Estás usando dos computadoras, Hugo?
No.
¿Dos pantallas?
No, solo una. Solo una. No sé por qué. Esa imagen de la Tierra yo no la tengo. ¿Cómo le hago para quitar la imagen?
¿Sí está viendo el problema? Sí, parece que tienes un fondo virtual. Se dice, a ver. Selecciona en el video de Zoom y parece que ahí tienes la opción probablemente tienes un background virtual en la cámara de Zoom.
Desenfoque. Si le pongo ninguno.
¿El video? ¿Me puedes ayudar? ¿Qué seleccione?
Ahí en donde dice cámara, donde dice dispositivo de video.
Dice cámara. No, cámara.
No, ahí está bien. Pero ahí. Sí, ahí. ¿Es una computadora de escritorio o tiene una cámara integrada en su equipo?
No, es la computadora, es una laptop.
Y al parecer es un problema con su cámara.
El icono de cámara
El teclado tiene un icono de cámara.
A ver, voy a entrar.
Su computadora tiene una tecla donde tenga una cámara, doctor, donde la desactive y la active.
Creo que así me parece.
En el teclado de la computadora.
Voy a entrar con otra.
Generalmente la tecla F8, doctor, puede activar y desactivar su... Ahí está.
Ah, listo, listo. Ahora que haga que... está. Listo. Vamos a comenzar. Jóvenes, vamos a comenzar porque ya estamos atrasados 5 minutos.
Sí, ok.
Good afternoon. It's a pleasure to introduce Dr. Garcia Compean from Cimpa. Dr. Compean is going to deliver a short course on non-Archimedean string amplitudes. Welcome, Hugo.
Thank you, Wilson, for introduction. And I would like to thank the organizers for the invitation to give this talk. I'm going to give two talks, and today I'm going to give a general description of the scattering amplitudes in general. I mean, it is independent of any field theory or any string theory. There will be general characteristics of general amplitudes, but it can be related to any specific field theory or any specific string theory. So today I'm going to give the general remarks about scattering amplitudes. Okay, on Monday, the next lecture, I'm going to apply this to non-Archimedean scattering amplitudes in string theory. Let me reduce this. And in the last part of the second talk, I'm going to give a brief overview on our work. I mean, the regularization and the limit P goes to 1. And hopefully, if we have some time, I'm going to speak about the introduction of an axionic B field. Okay, this is the content. And for this course will be very useful. A preliminary material is notes by Jose Antonio Vallejo called Introduction to Relativity and Quantum Mechanics, a crash course for math students. So this material is in the homepage of the conference, and you will find this there, together with the couple of talks. So the work was carried out by collaboration with Wilson, Professor Wilson Zúñiga, and Miriam Bocardo Gaspar, Edgar Lopez, and Angela Fuquén-Tibata. In particular, I recommend the talks by Angela and Edgar. I understand that Angela gave a talk yesterday, and Edgar, after this talk, he will speak. Okay, well, I'm going to give some generalities about the scattering amplitudes. So we will deal with a collision process of particles in field theory, in particular in the context of a relativistic field theory. And we will work with Minkowski in a Minkowski space-time. The Minkowski space is a 4-dimensional manifold, Lorentzian manifold. Lorentzian because it has a metric in order to measure distances, but the metric is not Euclidean, it's not positive definite. So it is symmetric because it is degenerate. It has a negative sign in some of the coordinates. So the signature will be in particular this one, -1 for the temporal coordinates and +1 for the spatial coordinates. Okay. So the scattering process of particles is a relativistic process. We will be interested in a relativistic process, but there is also a counterpart in non-relativistic quantum mechanics. But this is also a quantum mechanical process, evolution process, and it is determined by a linear operator in a certain vector space, acting in a vector space. And this operator is called S matrix or S operator. And the space is, the linear space is called Fock space. Fock space is a direct sum of tensor products, symmetrized tensor products of Hilbert space. H is the Hilbert space, and this is a graded graded vector space. Okay, the tensor, the S matrix or S operator, acts on particular if we have a tensor product of n times of the Hilbert space, the Hilbert space of one particle states. So it will be an Hilbert space of n particle. If the particle is a boson, we have to symmetrize, completely symmetrize the tensor product. Or if we have a fermion, we have to take the complete antisymmetrization of the tensor product. But we will work with bosonic, in the bosonic case. So the S operator acts in an element. This is the Dirac notation. This bracket represents a vector in this Fock space. So if you have an initial state, this operator will evolutionate this state into a final state or final state. Okay. Okay, we have this scattering process here. We have n particles in the initial states, in asymptotic states with t goes to -infinity. So the states are characterized by momentum of the particles and masses of different masses of the particles. So the line of time goes in this direction. So these particles meets and find an scattering center. Perhaps here will be a potential Columbian potential. So these particles will scatter in the final states, given by another momenta, P1 to Pm prime, and perhaps with a different number of particles. M and N are not necessarily the same, it's not equal. So the process can create particles or annihilate particles. So the evolution operator then precisely takes state of these incoming particles into outgoing particles. Okay, more specific, these states and n particle states for incoming particles are written in terms of the momentum, three momentum of the n particles, and specifying the precisely the incoming particles, the initial process. This is the initial process. This will be the final process. Okay, this is the state for the incoming particles, and the corresponding for the outgoing particles are given in this. Okay, the momentum with this in this vectorial notation are momentum in R3. R3 momentum in R3. Okay, in relativistic, the process is relativistic, so actually we have for momentum, a momentum, a vector in the Minkowski space. This momentum has with component by component 0 the energy, and by vectorial component the three momenta. So the P0 is the energy indexed by Greek indices. So we have actually a vector in the Minkowski space. The Minkowski space with the Minkowski metric is given precisely in this way. So these vectors multiply. The inner product is given by this. So this is a scalar from the is a relativistic scalar. So this is an invariant, Lorentz invariant, and this is the rest mass. So we have which is fixed in the theory. So it will be an Lorentz invariant. So from this condition, we have the energy formula for the relativistic mechanics, in terms of the three momenta of the particles and the mass of the particles, the rest mass. So the energy is the square of the energy is the square of the momenta plus the rest mass. Okay, so we have a formula for each particle. So this I index runs from 1 to n being the number of particles. Okay, so we mentioned that this linear operator gives is an evolution operator from the states in the initial for the incoming particles to states for the outgoing particles. So these states will be will form a basis in the Fock space. It's an orthogonal states. It can be shown that this is possible. So in this base, the S matrix can be written in this form. So the S matrix is in this notation, in Dirac notation, is written as the elements of the S operators gives the S and matrix n by m given in these terms. This is an element matrix. So this is a different ways of write down this. The transition probability, this is wrong. This is, the order is changed. So with the S matrix, it's possible to construct observable quantities. In general, this S matrix is a complex. The entries of the matrix are complex, but the transition probability, the elements are real numbers, and this gives the probability to give a transition from some n particles initial states to n particles initial final states. This is a transition probability determined by the S matrix. So it's a dynamical process. This depends on time. So this probability, one condition is necessary condition is that the probability is conserved in time, the interpretation of probability. So in order to do that, this S matrix should be an unitary matrix and satisfy this condition. Okay, this is some features for the S matrix. For a process with some short range interactions, the S matrix can be, the S matrix elements can be written in this part, in this form, where this is precisely the part of where the particles are not interacting and separated with the particles of a part which gives the complete interaction. So in terms of the S matrix, we can define the scattering amplitudes. The scattering amplitudes are in general also complex functions. It's a complex functions. Okay. It is very important. A very important property is the Lorentz invariance. So this is scattering amplitudes should be Lorentz invariance, and it will depends on only on the will be Lorentz scalars. So we have the only way that this will be an scalar is just the inner product of two momentum, and the rest must. So the scattering amplitudes will depend only on these quantities. Okay, this is a complex probability is real, but the amplitude in general is complex. It's a complex function. So the momenta can be complex also. So we promote in the physical system, these momenta are real functions, but real vectors actually. But in the scattering amplitudes, this can be complex. So we promote this to a complex function. It's our complex value. Okay, so in such a way that the restriction of this amplitude with the complex momenta to the when the imaginary parts of this cinematic part are 0, we will recover the physical amplitudes. Okay, another feature of these amplitudes is this is a complex function, but cannot be a holomorphic function in the whole plane, because due to the since the Liouville theorem, it will be constant. So it cannot be holomorphic. At least will be a meromorphic function, and the amplitude will have some singularities, some poles. Singularities in this particular case will have poles and cuts. The poles are given by singularity are dots in the real axis, and the cuts are this amplitude is a multivalued function that will have some cuts. Cuts are associated with thresholds, multi-particle. If it is only cinematically allowed to make n final states above a certain squared center of mass energy. This condition is very important because you need at least the certain quantity of energy on the center of mass in order to have a final state composed with n particles. So center of mass energy corresponding to the n particles. So this is a condition of the certain minimum energy to get a final state. Okay, so we have that the other are the poles. The poles are associated with single particles, and it is given by a singularity of the value of the momenta for the certain values of masses. This is associated, the poles associated with the values of the masses. Okay, I will go back this later. So in summary, the S matrix must be a complex function of Lorentz scalars. And the amplitude has poles and cuts associated with bound states, or the states associated with particles of certain values of masses. And the cuts are associated with multi-particle thresholds. For instance, if you have in this part, you have a center of mass of two particles, most you will have a final state of two particles. It's impossible that you have a final state of three or more particles. So this is the physical meaning of this condition. So knowing the singularities structures of the amplitude, it is a crucial prerequisite to being able to analytically continue this function. And the other condition is The ability to continue the function to different regions of their cinematical variables allows to conclude that the amplitudes for different processes scattering process are in fact related. We will give an example in the following. Okay, let's move to physical regions and crossing. Let's consider an amplitude with complex momenta or real momenta. This is not important for the moment. So not all the regions of the plane are cinematically accessible. You only have certain regions of the space of parameters of the cinematic momentum where the amplitude has a physical meaning. Okay, let's going to give an example of two scattering process. It's a scattering process of two particles into two particles. The time is in this direction. Is from the left to the right, the orientation of time. So the initial states are particles with momenta P1 and P2, and the final states are P3 and P4. So we have the process dependent of the momenta P1 and P2 goes to this process, to this final state. We'll consider all the masses of the particles equal, and it will be M for all of them. Okay. Introduce the Mandelstam variables. The Mandelstam variables are P1 plus P2 square, T is P1 plus P3 square, and U. This is interpreted as the square total energy of the center of mass frame. If you take a frame of which is the center of energy, so P1 and P2 are at rest. So the system at rest, we will see the masses of the particles, the rest mass. So here is the rest mass, and P1 and P2 has the vector component has to be the inverse one each other. So P1 and P2 is in the center of mass energy, is the center of mass energy. This is the interpretation. T is the other Mandelstam variable, is the total momentum exchange between the incoming and the outgoing particles. P1 and P3 is precisely the transference, the difference of momenta between the momenta of the incoming particles and the outgoing particles. This is a transfer of momenta. So, for instance, if S is greater than T, so we are in the center of mass frame. So T is the transfer of momenta from the incoming particles to the outgoing particles is very small. Okay, so the theta is the angle between P2 and P3, or P1 and P4. Okay, in addition, we had some conservation laws of which the sum of momenta, relativistic momenta, 4 momenta, is equal to 0. So this is conservation of 4 momenta, is conservation of energy and momenta, and 3 momenta. And another condition that the sum of the Mandelstam variables give precisely the rest mass with a factor here. This is conservation laws. If you have any question, please just interrupt me, please. Okay, we want to determine the region of the in this space, in this cinematic space, that corresponds to scattering, to physically allowed scattering. Okay, so in the center of mass frame, we have thus just P1 and P2 satisfy this condition. The energy is the same, but the momentum is not positive. The 3 momenta is in a positive direction, and the energy is the same. So for the outgoing particles, this is something similar. The 3 momenta of these two P3 and P4 are opposite in direction, and in the magnitude is the same. So we have, and the energy is different. If you substitute this in Mandelstam variables, you will get this set of variables in terms of 3 momentum masses and the theta angle, which is precisely the angle in this frame, in the center of mass frame. So these are the Mandelstam variables for this 2-to-2 process, scattering process, with all the masses equal, and in the center, in a particular frame, which is the center of mass frame. Okay, the physical scattering occurs precisely when the energy is positive definite. This is because it's not possible to have negative energies, and the angle is bounded in this in between -1 and 1. Okay, so these conditions, which determines the physical scattering in terms of the using these equations here. So in terms of the Mandelstam variables, these are these conditions. So this is called the S channel. This is S channel, where the center of mass is precisely in the S variable. The transference of momenta is very small, so we have bounded, limited T and U variables. Okay, so let's change a bit this diagram. Rotate this diagram in this case. So the rotation can be obtained by change these variables into these variables. So the first diagram, the charge of these particles is given by the first equation, and the previous one is this is given by this equation. So we have a system of equations, and the solution, the unique solution, is precisely that the charge of B bar is minus the charge of B. That means that C bar is the antiparticles of C, and B bar is the antiparticles of B. So we have rotation. Essentially, we will have the same diagram, so the scattering amplitudes will be the same. It's only a trick. But for this diagram, the scattering amplitude will be given by this in terms of t. So this change is precisely that the interchange of S and T variables. So we will change from the S channel to the T channel, and the condition in energy are given by this equation. We have change by S and S by T, and then so those two conditions are interchanging. This is precisely a different region of the cinematical region. So in principle, this scattering amplitude should be different. But due to the symmetries of the change of particles by antiparticles and the momenta to change the momenta in opposite direction, we will have actually that this diagram is essentially the same that the previous one. So the amplitude will be the same. So the region of the parameters of the cinematic space is different, but the amplitude is the same. This is called the crossing symmetry of the amplitudes, and this will be important. In principle, we have to do the same thing with the. This is I'm sorry. This is the T channel. The process with the T channel. So the crossing symmetry interchanges the S channel with the T channel, and in addition, it's possible to carry out the same thing with the channels S and U. And we have something similar, so that there exists also a crossing symmetry. So in principle, we have three channels: S channel, T channel, and U channel, where the amplitude is a different regions of the space of parameters, cinematic parameters. So due to the crossing symmetry, these channels, these regions will give the same physical amplitude. So this is a symmetry in the scattering amplitudes. It's very important symmetry. Okay, so we move to the Ricci limit. The Ricci limit is to consider the high energy limits for the previous mentioned scattering amplitudes. We will continue for the two scattering two particles. So in this limit, the center mass energy is much more greater than the transfer of momenta and the mass of the relevant mass of the particles. In this limit, it's possible to show that the amplitudes in this very high energy limit, the amplitude has this structure, which in principle seems to diverge for J positive number and greater and greater number. So the important thing here in this structure is that the large limit in the S channel implies an interchange of particles in the T channel. So we have the S channel, the S channel is very high energy. We will have interchanging particles in the T channel. So the amplitude will have some poles in the S channel. If we take this sum goes to infinity, if you have an infinite number of particles, so in principle, this is not possible that this formula gives some poles in the S variable. This has poles in the T variable, but not in the S. So this is very important to assume that this formula is assumed from 0 to infinity. In this case, it's possible to find some kind of symmetry between S and T. This symmetry is motivated by the crossing symmetry we mentioned before. So in order to implement crossing symmetry in this formula, we have necessarily that this sum is an infinite sum. Otherwise, it's impossible to establish some symmetry, some crossing symmetry in this form, in the high energy limit of the scattering amplitude. So the crossing symmetry implies that we can interchange S channel by T channel, and we will have this formula. This kind of formula is also possible. In the 60 years, Gabriel Veneciano proposes a formula which precisely has this symmetry. It's the asymmetry or the crossing symmetry between where it is possible to have this equality. This symmetry, this formula is in terms of gamma function, Euler gamma function, and where alpha of S, alpha of T are called a Rey trajectory. It's a linear function of the Mandelstam variables, and alpha prime is the Rey slope. It's a slope. It's a linear function that alpha in zero is given by experimental data. This formula is very important because it has this crossing symmetry. This has the automatically. Sorry. So, for instance, you can expand. You can take. It's possible to show varying S and fixing T. You will have from this equation. You will have from this. It's possible to obtain these poles, and the behavior of this part is given by the rest of the numerator of this formula. So, but we will have take this pension will have poles from this equation. We'll have explicitly the interchange of T and S channels here. So this formula proposed by Veneziano realize explicitly this crossing symmetry of the in the radial limit of the. This formula is very, very important. In here, we have, for instance, in the 60 years, we have the interchanging of interacting of, for instance, baryons, and sorry, let me put the battery. Okay. For instance, the interacting of baryons in the S channel is described in terms of the interchanging of meson particles in the T channel. So, in principle, in the 60, this sum is not necessarily goes to infinity, because this sum is in principle a sum over the number of baryonic and mesonic particles, which are finite in principle. But if you have this, it's not possible to have the crossing symmetry in here. So it's necessarily to have an infinite sum. Okay. Veneziano formula is in the 60 years. Some people like Susskind and Montonen, they proved that it's possible to extract this Veneziano formula from the theory of strings. So I'm going to move in this direction. If you have any questions about the previous thing about the scattering amplitudes, please go ahead.
Do you have questions or comments? It would be a good idea to have a small break after 55 minutes.
Okay.
To have a break, a short break, after 55 minutes, 1 hour.
Yes.
You have 2 hours.
Okay. Okay. Well, we continue. So let's move on to open strings. Let's consider now the variational principle in the open string context. The string theory, in string theory, we have a theory for an embedding map, which states a Riemann surface with a genus G, B number of boundaries, and N market points. And this is a mapping to any Riemannian manifold. And we will have, in general, is a d-dimensional Riemannian or semi-Riemannian manifold. But here we will take the Minkowski space-time. So this RD is the Minkowski space with the Minkowskian metric. This will be enough to us to our aims. Okay. This it has a non-empty boundary. So the local coordinates on this surface is sigma 0 and sigma 1. Sigma 0 is called tau. It's local coordinates on the Riemann surface. And sigma 1 is sigma, just sigma. So this is a cartoon of this embedding of the Riemann surface with one boundary and genus 3 and 5 market points. Okay, into the Minkowskian space-time. So the variational principle is given by an energy integral or action. The action has two parts. The first part is given in terms of this vector mapping. This vector mapping X is the embedding, and we have two parts. This part is not necessarily here. This is only for completeness, but if you can take B equal to 0. So this action is eta is the Minkowski metric in the target space. A few notation. This is the worksheet. The Riemann surface is called the worksheet, and the Minkowski space is precisely the target space. Okay, this action has symmetries. For instance, it has a diffeomorphism symmetry. H is the metric. H is the inverse of the metric on the worksheet. So it has the symmetry of diffeomorphism on the worksheet. And has a Poincare invariance in the target space because it is a Minkowskian space. It has X can be translated, rotated, or can be acting on the Lorentzian transformation. So we have variables. So this is a theory on the worksheet in two dimensions. But the fields of this theory, it can be interpreted as coordinates on the Minkowski space, target space. Okay. So T is the tension of the string in terms of the inverse of the Reye slope, alpha prime. Alpha prime is interpreted as the size of the string. This action describes the action of the motion of a string in target space. Sorry, there is another symmetry that I omit. Very important symmetry is precisely the conformal symmetry on the metric on the worksheet. It's a very important symmetry. The conformal symmetry, the diffeomorphism symmetry, and in the target we have the Poincare symmetry. So the degrees of freedoms of the theory is X and H. X is the fields, scalar fields. There are as scalar field as the number of coordinates on the target space. And H is the metric on the worksheet in 2 dimensions. Okay, so the Minkowski metric has the signature as the previous situation for the scattering amplitudes in field theory. Beam eta is is a symmetric tensor, is in the target space, and B mu is a tensor, is an antisymmetric tensor in the target space. So the target space is of dimension D. So, well, this is the first action. The second action, S prime, is given by, we can add to this action a topological action, which in 2 dimensions consists in the Euler characteristic of the Riemann surface, and perhaps with some boundaries. Okay. The B field, the integral in the worksheet is precisely a total derivative. So in terms of the A variable, this variable, you can write down this expression as, in terms of integration using the Stokes theorem. You can write down this action as in terms of the integration on the boundary of the Riemann surface. In terms of the A variable, is precisely given by this. It's given. So this is precisely the pullback via the embedding X to the variable A. Is the pullback. A is a field on the target space. So this is precisely the pullback to the surface, to the boundary on the surface. Okay, where we have this action, we have this is the variational principle. We have equation of motions, the Euler-Lagrange equation of motions, which they will be not important here. So, this equation satisfies these Neumann boundary conditions. In this equation can be solved, but they are not important here. Okay. So the boundary condition, in principle, let's, in order to be more specific, let's consider an open string, this here in red, this is an oriented open string of size pi, from 0 to pi. So this strings is propagating in the target space. So the boundary of the string is given by this line in black color. So this open string, non-interacting open strings, the coordinates on the string is sigma, and this string is moving in time in this direction. The coordinate is tau. This is the worksheet, and a specific worksheet in 2 dimensions. So in complex variables, we can take W given by this variable, and we can perform a conformal transformation from this W to C variable. And the C variable, we have that the boundary of the strings is mapped into the real axis. We have here the half complex plane in terms of the variable C. So we have here coordinates C and C bar. And the boundary condition of Neumann boundary condition is precisely the P, the pi, and 0 translate in this diagram in the imaginary part of C variable equal to 0. So the boundary is here, and the strings are mapped into two market points in this boundary. You have that this under another conformal transformations, you will have perform a transformation to transform this into the disk. Okay, the string oscillates along in longitudinal direction and transversal directions. So this oscillation can be quantized, and the quantization, the quantum modes of this generates a representation of the Poincare group in the target space. This is very important because the target space has the Poincare symmetry, and you have there an invariant state determined by the momenta and in principle the vacuum of the number of oscillations. So the string may oscillate. This is the bosonic string, the bosonic open string. So we have a number of modes of oscillation. They are quantum oscillations, and the lowest mode is precisely a mode with mass square negative. So we have a tachyon. We have a tachyon, a particle with mass square negative. So this in the bosonic string, this is a problematic situation, but in the super strings, this mode is removed by the symmetries, by the supersymmetry. So in principle, this is a good, the simplest state, and many of the characteristics computed with tachyons will remain to the other more complicated states. So in principle, we will take this precisely, we will work with this mode, the lowest mode of the open string. Next mode is corresponding to a vector, a massless vector with mass equal to 0. And the other modes are we have a infinite tower of particles with mass, with very high masses. So the important will be the tachyon here. Okay. Another is that the critical dimension of the target space will be 26 for the bosonic open strings. Okay, with the states, we can construct vertex operators. The vertex operators are observable quantities in the theory in order to compute the scattering amplitudes, and these operators are should have the symmetries of the theory. There should be the diffeomorphism, diffeomorphic symmetry, and conformal symmetry, and Poincare symmetry. The three symmetries are present here in this vertex operator. So it's very important that these operators, in order to be invariant on the diffeomorphism, should be integrals in the worksheet space-time. So depending of the state of the theories, if you have a tachyon, a massless vector, or any other particle, we will have different function in here. And for the tachyons, this function is just one. Sorry. And for the other particles, it's a bit more complicated, but in principle, this complicates the scattering amplitudes, the computation, but take the tachyon vertex operators will be enough for us. Okay, the tachyon mass is mass square is precisely negative, and it is given by 1 over alpha prime. This is for the case of open string. For closed strings, we have another situation. Okay, the interactions of the open strings. Sorry. The interaction of the open strings, trying to imitating the diagrams of the initial diagrams in the beginning of the talk. We will have two asymptotic states that will interact in some region, and there will be a scattering of the strings, and we will have a final states, asymptotic final states. So in principle, in these strings, we can associate a vertex, one of these vertex operators. We will take the tachyon operators with momentum k. So we will have vertex operators in all the associated with this one of the modes of the oscillation of these strings. You can, of course, take another to change the vertex operator to take vertex operators of massless vectors or massive particles, etc., etc. We will take the vertex operators associated with the tachyons, and the momentum is precisely the momentum in here in the exponential of here. So under a conformal transformation, this diagram is the boundaries map in this is the disk with the boundary and four market points. For market points where we inserted here the vertex operators. For instance, the tachyon vertex operators, in order to be specific. So the evolution of time is in this direction. So we will have, from now on, diagrams with, we will take the disk with one boundary and with four market points. And these market points we will take for tachyonic vertex operators. This is another representation. This is if you have this, you have maybe more boundaries. 1, 2, 3, 4, 5 boundaries. One more boundary than the previous case. This is mapped precisely to this diagram. This is a three-level we have the genus is 0 in this situation, and we will keep in this situation, but in principle, one diagram with the genus 1 is given in this case, where two boundaries are associated with strings 1 and 2, and the other boundaries are associated with the other strings. So in order to perform an scattering process, we will have to necessarily to give from one circle to another one. This is the one loop diagram, and this kind of diagrams are not deal in these lectures. We will keep in diagrams like this, more specific in the disk. We will work with the disk. Okay, scattering amplitudes can be obtained by the correlation functions of n vertex operators in general, and from the from this action for S prime in terms of the Euler characteristic, we will have this structure of the scattering amplitudes, where lambda S is the exponential of phi 0, and this is the genus minus the Euler characteristic of a Riemann surface with the boundaries. So we'll take here B equal to 1 and H equal to 0. So, but you can, this is the general form to compute any a general scattering amplitude for an open on a closed string theory, depending of B, G, and N. N is the number of market points. This quantity here in here, depending on lambda and K, is the amplitude for n points, and this is given by a Feynman functional integral, where X are the embedding map, H is the worksheet metric, and lambda, we will have the insertion of n vertex operators. So n in this case will be 4. We go back to this situation for the disk. The disk with 4 points. That means we will work with the three-level amplitudes. In general, M is the model space of Riemann surfaces of this with these characteristics. But the three-level amplitudes that will be interested for us are precisely this one for endpoints, amplitude for endpoints. Okay, we have the symmetries. I mentioned the symmetry of diffeomorphism and worksheet symmetries, diffeomorphism and byte transformation of conformal transformations. For instance, for closed strings with their boundaries, for closed string in where the number of boundaries is 0, we have that this metric, this worksheet metric can be fixed by these symmetries. But the fixing is not complete. There are some remaining symmetry that cannot be fixed, and this symmetry is precisely for the closed strings. Is a global symmetry. Is SL2C symmetry. So this symmetry, with this symmetry, we can fix the symmetry for the metric. I mean, this worksheet metric can be transformed in the metric of the plane metric on the worksheet, but there will be a remaining symmetry that. So the scattered after fixing symmetries, worksheet symmetries, there will be a remaining symmetry that for the closed strings is this precisely this symmetry. This is called also the conformal killing symmetry. And we will have two copies of this symmetry. One for, in the closed string, we have two sectors, the holomorphic and the anti-holomorphic sector. And we will have two copies of this symmetry for the closed strings. So this symmetry will be present in the scattering amplitudes after gauge fixing. So this symmetry is the Moebius symmetry, where A, B, C, and D are complex variables satisfying this condition. So this symmetry can be useful in order to fix 3 points on the sphere. That's that we call 0, 1, and infinity. This is just to give a number, a name for the points where we can fix the points for 3 points where we can put here a vertex operator. Sorry, this is the case. In the case of closed strings, we can choose these points for any point of the two sphere. In the case of open strings, the Riemann symmetry, which preserves the boundary, is SL to 2R. Is a reduced symmetry. Is a lower symmetry than the open, than the closed case. So in this case, we will have that this remaining symmetry allows to fix 3 points in the boundary on the disk. This is possible if, in absence of the B field, if you have a B field, this symmetry is broken, and then it's not possible. It's impossible to fix 3 points with in the presence of this B field. Okay. Let me take that. Well, so in order to compute the scattering amplitudes, we will go back. We will compute scattering amplitudes. We have to put the disk, and we will take 4 or in general n points, in market points on the boundary of the disk, and in here we will have vertex operators, tachyon vertex operators, and compute the correlation functions given by the Feynman integral, the Feynman integration in the appropriated moduli space. So this is not easy in general. In physics, we use, in general, the path integral is not well defined. So we have to perform only formal calculations. By formal means to take the finite dimensional case of the Gaussian integration and to adapt this finite dimensional final dimensional computations to the to the infinite dimensional case, which is not a good deal, because but in principle many of the computation are result to be correct, but in general we don't have a rigorous way to compute this path integration. So because the measure of integration doesn't exist in general. In the Euclidean case the Euclidean case, the measure of the integration exists in certain cases. This is the I don't remember when this will be a probability measure, will be related to probability measure. Okay. If you hear the talk by Angela yesterday, she compute everything in a rigorous way, but this is a very complicated situation for each case. So in general, it's a very difficult problem to solve. So this is I think it's an open problem. Well, in the case of when you have a B field with B constant, the equation of motion can be solved in terms of the green functions and with the Neumann boundary condition I mentioned before. So the result of this computation is a partial differential equations computation in 2 dimensions. So the result is this complicated because we are including the B field. So this is the green function it's a solution of the equation of motion. So this G and theta, G is related to the metric, the induced metric on the target space induced by this by the metric, original metric in the target space. This G is the Minkowskian metric. So K is a green function which satisfies this equation where delta is the Laplace-Beltrami operator. Okay, but the way to find this the correlation function or scattering amplitude is to write down precisely in terms of this green function. The structure of the path integral is of the Gaussian type. It's a Gaussian type. This come from the equation of motion, and this part come from this, the tachyon vertex operators. So in fact, we can complete the square of this integral to find this is to transform this integral to a Gaussian type integral, and to find precisely that the integration is given. After integration is given, formal integration is given in terms of the green function and J. J are is a current. Here is interpreted as a current multiplied by the field. But in the case of interest here, J are given in terms of this part come from the vertex operators, tachyonic vertex operators. So if you take J induced by these vertex operators, so this part come from, let me, the substitution of the vertex operators, and recall for the tachyon, the vertex operators are the exponential of ikx. So for each particle, we have one copy of this. For n particles, we have all this. So, taking, if you take J as precisely these K parts of these vertex operators, and with an appropriate, inserting an appropriate delta function, so we can put this integral in terms of, in this way, so we can formally to perform the integration and to give this form. This is an integration over all the embeddings, over all x. So the result is independent of these fields. Okay. Recalling that the vertex operators are on the boundary of the disk. We have only one variable here. It's tau, precisely tau, the coordinate. So we can put these operators in for various values of zeta equal tau. So for instance, the green function this green function for this case reduce to these two terms. This theta depends on B. If you take B vanishing, the B field, you are not interested in this field, you can take this to 0, and you take only one part. So using this expression and working out this integral and taking the integration over the boundary of the disk in terms of n variables, the n variables given by the real variables of tau 1, tau 2, tau n, because we are working with endpoint scattering amplitudes. So it's possible to transform the correlation function or scattering amplitudes in this way. this integral is of the Kova-Nielsen type. If you are not interested in the B field from the beginning, so you should be this equal to 0. So this exponential is 1. So we have the usual case of open strings. These points, these taus are points in the precisely in the n-dimensional space, real space. Tau are real variables, and this exponential is a kinematic, is in terms of alpha prime, the Ricci slope. G is the induced metric, and K are the momenta of the vertex operators. So this is a kinematic factor here. In here, we have the Minkowskian inner product. In here, we can remember K has another index. I is the index of the number of particles, and mu is the index of the coordinates of the target space, or the coordinates of the Minkowski space-time. That in the string, in the particle physics case, we have from the beginning 4 dimensions, but in the string, bosonic string, we have 26 dimensions. Okay, those we have a more complete scattering amplitude for the open string. And for the case of, in the case of the B field is vanishing, G is the Minkowski metric. So the previous amplitudes. This factor will be important because in the case of Gaussian and Kawano amplitudes, they have a constant non-vanishing B field, and this factor plays a very important role. But on Monday, I will talk about this. This is precisely, this is in the Fourier space, but if you take if you go back to the space-time variables, this is precisely the Moyal product, which appears in non-commutative geometry, in non-commutative field theory. So the B field in this situation turns out the amplitudes in this space, in this n-dimensional real space, into a non-commutative n-dimensional space. So this factor is very important. This has very important information. But from now on, we will take here this factor equal to 1. So taking the B field equal to 0. And in this case, we have the n-dimensional space, n-dimensional space, but recalling that we have the open string case, this Moebius symmetry permits to fix 3 points in the boundary of the disk. So 3 points, we take three of the vertex operators in some points. So we make this explicitly, and we fix 3 points. We will have an n-3 dimensional space. We will take here for the case tau 0. Tau 0 is precisely in 0. Tau 1 is in 1, and tau infinity is in infinity. We can remove this this factor. So the rest, these scattering amplitudes for the n integration in the n-dimensional real space on the boundaries, x tau is a boundary variable of the disk. So we can remove 3 points here. We keep with this expression, where this integration has an order. This is an ordered integration. So the integration is from 0 to 1. Is the integration along the size of the string. So this is very important. It's an ordered integration, and in these variables, well, for the case of 4 points, for the case of n equal to 4, this is n-point scattering amplitudes is precisely the Veneziano amplitude. The 4-point amplitude is precisely the Veneziano amplitude, which I mentioned before in the context of scattering amplitudes in field theory. Okay, and we have the exponents of precisely the scalar product. This is an Lorentz invariant quantities. And these amplitudes will be Lorentz invariant. And these cinematical factors are possible to be complex also. Okay, this integration from 0 to 1. Integration from 0 to 1 describes just one of the 3 decay channels. For instance, the S or the T channel, one of them, and this is because the ordering of this is a specific order of the number of vertex operators here. So in order to consider the integration independent of the order, we have to impose the sum over all the channels, the S, T, and U channel. And in this case, the amplitude is the integration is over all the real numbers, and the integration is not order. There is not a order here. So because we have in the case we should for the 4-point amplitude, you have this depends on the order of these points of where are the 3 or 2 of the vertex operators. So in order to have the integration independent of this, we have to consider the 3 channels, and in this case, this integration is independent of the order. So we have a different amplitudes, and that we have in this case the 4 channels of the scattering amplitude. Well, if you carry out these integrations, so it's possible to show. I omit here, but it's very easy using the beta and the gamma function. It's very easy to transform this to find the exact integration of this formula into the in terms of the gamma functions. This is ordinary gamma functions, real gamma function. They are not non-Archimedean or Piatic. So the three channels are precisely in the integration over R, where in this this is another very beautiful thing, that the cinematic factors transform into the definition of the Mandelstam variables. So we have precisely the Veneziano scattering amplitudes for integration of correlation function of 4 points for the tachyons in on the disk. I mean, for the three level amplitude. So this scattering amplitude, Veneziano scattering amplitude, has the three channels. So in the field theory limit, the expanding the gamma functions about the poles, certain poles, or this gamma function, or this, we will have the interpretation of from this is not correct, because this is it should be here the disk with 4 points. This is for the closed string case, but for the open strings is the disk with 4 marked points. So we will have the three channels, the three field theory channels, ST and U, and this is for instance, for the S channels, the interchanging particles here in the S channel are precisely the tachyon. The tachyon arising will be all particles in the spectrum of the theory. For instance, well, in this case, will be for the tachyon, but if you take another scattering amplitude, you will have another particles here. So the particles, and you can precisely compute in the poles the mass of these particles, and it is given precisely by the mass of the tachyon. The mass square of the tachyon, which I mentioned before. For the open string, the tachyon has mass square -1 over alpha prime. All this is consistent. It's very nice. And from the Veneziano amplitude, you have the crossing symmetry, precisely the crossing symmetry that I mentioned in the introduction material, in the introductory material of this talk. Finally, I want to mention that this procedure works also for the endpoint point particles. In this reference of KLT reference, Kawai, Llewellyn, and Tide, they show that is this the trick here by the integration, the consideration of the three channels made this integral independent of the order, works also for the n-dimensional case. So we can define the integration over the R n-3 real variables on the boundary of the string, of these are inserted points on the disk. Okay. For the closest string, for completeness, we have only the insertion of the vertex operator will be on the sphere, the complete sphere. So see, we will have a two-dimensional case, not here is just one-dimensional. Here is two-dimensional. We have, and for the closed case, is the amplitude is the Virasoro-Shapiro amplitude, which is very similar to the case of the Veneziano amplitude. In this paper, sorry, in this paper, KLT, the conjecture, this amplitude is the square, the Virasoro-Shapiro amplitude for closest strings gives is precisely the square of the Veneziano amplitude. So the closest string case is the square of the open string amplitudes. This is a conjecture valid for tree level, for diagrams without loops, and it is a conjecture for in general, for the general case, for any integration over any loops of in string theory. Okay. Finally, I should mention that there is another way of remove the dependence of the order, starting from these amplitudes, with where the operators are ordinary integration from 0 to 1. It's possible to remove the order by introducing, there is another way, by introducing this design function. Design function is a function is given by, is 1 for x positive and -1 for x negative. It's a step function, or this is also called step function. So this integration, introducing these variables is possible to transform the integration with an ordinary particles to remove the order. And generalization for endpoints of this is also very easy to carry out. So this is the result. As mentioned before, the introduction of a constant B field will be important in the context of Gauss-Alcahuano amplitudes, but on Monday I will work with these amplitudes in the context of Piatic strings, string amplitudes. So this is my last transparency. So in summary, we have to give the general remarks about the scattering amplitudes, general properties, independent of any field theory. They have to be Lorentz invariants. They have to be unitary in order to preserve the probabilities, and has to have the crossing symmetry, and in the context of strings, open strings, in the concrete case of open strings, the correlation amplitudes of 4 points give precisely the Veneciano amplitude, which reproduce these all properties of the of these properties, unitarity, Lorentz symmetry, and crossing symmetry. So another characteristic of this is precisely the region of where this symmetry. These regions are equivalent due to the crossing symmetry. So, for instance, to find the relation between these regions in the cinematic space for the end amplitude correlation function is a very hard problem. For the 4 points is more or less easy, but in general for the endpoint amplitudes is very complicated in the real case. So in the next lecture, we will restrict to the case of the Piatic scattering amplitudes. The Piatic scattering amplitudes will be constructed by changing the real norm by the Piatic norm, and to carry out the integrations in a split in the explicit form for 4 and 5 points. In the Piatic case is more or less easy to compute, but different for the real case in where is still at the level of conjecture to give a region where this integration exists. For the real case is not we have only that this integration exists is convergent only for in certain cases. In general, it's impossible. In the Piatic case, we will see that the possibility to find a general way to find the region of the space of in the complex cinematic space of this momenta is possible to carry out this to prove this a theorem related with this. So the problem is computing these scattering amplitudes in general is an open problem for the real case. So in the Piatic case, we give some general remarks. We will give in the general remarks that helps to find a solution for the real case. So I should stop here. Thank you very much for your attention. There is time for some questions. Please go ahead or comments or anything you want.
Okay, first of all, let's ask to the speaker. Are there questions or comments for the speaker? Okay, just let me remind you that in the paper, in our paper, not in my paper with Ricardo Gaspar and Bayes, we established the case of, the existence of region of convergence in all the cases, the Piatis, the real and the complex cases.
Sorry, in the case of
No. See, yes. In the paper in Journal of Higher Physics, I don't remember 2020, I think.
Yeah.
We consider the case a real complex and Piatic case using resolution of singularities.
Yes. This is the paper by Miriam Bay and you.
Yes, based on me, yes.
Yes, in this case, this is a very important result because it's possible to imitate the case, the proof, the theorem for the Piatic case. Not only these arguments are valid in order to find the convergence of where this integral is well defined. This integration is transformed in a local zeta function. This has the structure of local zeta function, and it's possible to find a region where this local zeta function is well defined, can be written as rational functions of Piatic rational functions, and it can be found explicitly the integration region. So this is for the Piatic case, but in this paper that Wilson mentioned, these methods were used in general for real or complex case. So this is an integrating treatment of the real and Piatic. Is a very surprising. It's a surprise that these methods valid for the Piatic case can be extended to the real or complex. The complex case is the amplitude I mentioned before, the amplitude of the closed string. Sorry. I don't. Okay, here, the closed string, the complex case. So not only for open strings, but for closed strings. But I will say more about it in the next lecture.
Okay, thank you very much. Let's thank the speaker again. Thank you, Bruno. See you on Monday. Now we have a break, 30 minutes break before the last conference. And remember, today at 7 p.m. we have a taquiza somewhere. Okay. In the terrace, in the place where we take the lunch every day. Okay, guys, let's take a break. ¿Todavía me estás escuchando, Hugo?
Sí, Wilson, aquí estoy todavía.
Oye, a ver si sacamos un tiempo para, ya que está Edgar acá, no sé si, yo me voy el martes, a ver si sacáramos un tiempo para hablar de las superamplitudes, a ver qué me cuentan, a ver si hacemos eso también, no sé cuándo. Yo voy al Cimpa, el primero, ¿cuándo es? Ángel, ¿cuándo es su defensa? El 1 de junio, ¿no?
Viernes, 3 de junio.
El 3 de junio. El 3 de junio yo voy a estar allá en el Cimpa, está la defensa de tesis de Ángel, que está a las 10. No sé si pudiéramos sacar un tiempo y hablamos. ¿Tienen tiempo?
Ok, sí. Sí. ¿Es viernes?
Sí, es viernes.
Okay.
La próxima semana. O sea, a ver si puede ser. Yo puedo llegar temprano. No sé, pero yo creo que la defensa es 1 hora. Podemos trabajar un rato y después vamos a comer con Ángel y con los jurados. A ver.
Ya, a ver si vemos algo similar. Sí, porque como les decía, necesitamos en la definición, o sea, necesitamos el punto de partida.
Sí.
Sí, o sea, estar seguros por lo menos que tenemos una referencia, una motivación. ¿Listo?
Ok, sí, está bien, Wilson. Tú sigues ahora, Edgar, ¿no?
Vas a asistir ahorita, habla después del break, habla. ¿Listo?
5:30.
5:30,
Ok.
bueno. Entonces nos vemos a las 5:30, Hugo.
Sí, nos vemos.
Chao.
Chao.
Bueno, de hecho, yo todavía tengo que cerrar el semestre.
Por eso le aconsejo que le
Ya,
Okay.
Guys, we are ready for the last talk.
Por favor, ¿verdad? Sí. Bueno, esto ya lo puede poner. Ah, tú lo puedes. Voy a esperar la hora.
It is a pleasure to introduce Edgar Lopez. Edgar Lopez is a young theoretical physicist. Edgar is pursuing his doctoral studies at Cimpa under the guidance of Dr. Hugo Garcia Compean. Today, Edgar is going to present the latest paper, his latest paper, titled Towards Non-Archimedean Superstring Amplitudes. Welcome.
Thank you. Do I need a microphone? Yes. Yes, hi. Thank you all for being here. I want to thank also the organizers for making this event possible. Yes, has been already mentioned. The title of my talk is Toward Non-Archimedean Superstring Amplitudes. This is my latest paper. You can find it over here. And it's a collaboration with my thesis advisor, Hugo Compean. Okay. First, I want to tell you a little bit about how we do theoretical physics. This is a very ambitious question, but it can be answered in different ways. But I will tell you, well, it's my perspective. It all starts with what we call an action. An action is a functional, it's an integral, where we have some fields, we have a physical interpretation for them, we have some fields. In general, we integrate over a smooth manifold and dimensions. This function is called a Lagrangian for some historical reason. And a basic thing that we can do from this action is to obtain the equations of motion. That is the equation that will govern our system, how it will evolve in time. And we do this by performing a variation, and that is an infinitesimal perturbation over the fields that are called delta phi. And we take this subtraction to order delta phi. I mean, we ignore all the higher order terms because we assume that the perturbation is small. And if we set this variation equal to 0, we get what is known as the Euler-Lagrange equations, which we interpret as the equations of motion for our system. Just to give you some notation right here, this just partial soft mu symbol. This is just going to be the partial derivative with respect to the coordinate x mu. And maybe you notice it in Compean's talk. There is always an implicit sum whenever we have repeated indices, one at the top and one at the bottom. We imply that there is a sum over a set index. So you will see a bunch of indices, but most of them are just summing on them. And they are the products. Okay. Oh, here. Yes. And again, talking a little bit about scattering amplitudes again, just to give you some intuition, we can think of a game of pool, where we have, well, at the beginning, we have the white ball that is going with a certain speed in a certain direction, and it's going to collide with a bunch of other colored balls. We configure it as the initial state is a white ball going with a certain velocity, and after the collision occurs, well, the balls get scattered and each ball acquires a different velocity and a different direction. And we characterize that as a set of final states or outgoing states. That's the intuition behind the scattering process in a more general way. And we have a set of incoming states. They interact in some way. They could be a collision, could be an electromagnetic interaction, some physical thing. And at the end, we have a set of outgoing states. And the scattering amplitude quantifies the probability of said process occurring. So given a set of initial states, what is the probability that we get a set of outgoing states that is captured with the scattering amplitudes in a given theory? Okay. Well, just a very basic way of how we get the scattering amplitudes. It was also mentioned in the previous lecture. There's an association that we have for states, physical states. We can associate to them vertex operators. That's the mathematical description. And the amplitudes are obtained by what is known as a path integral. As has been mentioned, this can be a little bit more formal, but it works in a certain way. And we obtain these, the amplitudes can be defined with the expectation value of the vertex operators, and we have as a weight the exponential of the negative sign of the action. And we iterate over the dynamical fields. This is just another example. Here's a set that is called the partition function. The names I think come from analogy with probability that we've seen in other lectures. They are very similar forms. Now, I want to tell you a little bit about what is supersymmetry. In my title, there was the word super. It refers to supersymmetry, sometimes abbreviated SUSY. Symmetry in general is a transformation that we can perform to our system and will not change the results. For example, I can do an experiment on this table, and if I perform it in another table, the result will be the same. That means it is invariant of the translation. It doesn't care where it is. There are lots of different symmetries, and they're very important in physics. And another thing you know is that there are basically two types of particles. One is named bosons, and the other are named fermions. That's all you really need to know. And supersymmetry is the symmetry we have in the description of these two particles. Basically, if we exchange the description from bosons and fermions, we get the same result or the same theory. And that's what we call supersymmetry. Mathematically, the variations that we can perform a variation where the variations of the fields describing the bosons will be proportional to the fields describing the fermions and vice versa. And if this variation is equal to 0, then we have supersymmetry. Okay. And just again, I want to tell you a little bit about what are Grassmann variables. Because we use it to describe fermions. Grassmann variables are the property that they have is they anti-commute. That means that if we multiply 2, we can exchange the order of the product at the cost of a minus sign. In particular, it will imply that a Grassmann variable squared is equal to 0. And this also implies that all functions will be linear. So for example, we have exponential is just 1 plus the Grassmann variable. And so the log of 1 plus theta will be just equal to theta. And note that for several Grassmann variables, in pairs they do commute. So if I grab a pair and I commute it, we don't get a negative sign. This is just because we would get a negative sign changing 1, and we change the other, we get a negative sign, and we get a plus sign. We can also define some operations of integration and differentiation. I think the integration is mostly a definition. I think there's a measurable. But we can, they're defined this way. The integral of theta, d theta is just 1, and the integral of simply d theta is 0. And the derivative, well, it's much more intuitive. And an identity I want to show you is if we have a Grassmann valued field, we can manipulate using the Grassmann rules, manipulate to be given in this form. From this rule, we can see that these two things are equal. So we can write it as an exponential with an auxiliary variable theta. It will be useful later. Okay. Okay, that's the first background. And we move on now to what is Piatic string amplitudes. Well, this has been mentioned before, but Igor Belovich conjecture in 1997 that the Piatic scale, which is a very small scale. Sure.
Yeah.
Yes.
I'm curious about the definition of the integral, because I'm thinking maybe the integral of theta should be theta squared, that is 0, but you put 1. What is the reason that you put 1 and 0?
Take it more as a definition. Because, well, the short answer is that because it works. We can do the things we want, we define it this way. Take it more as a definition of an operator, not really an integral. And well,
notice that you cannot get theta squared because theta squared is 0. You see, that's the point.
Yeah. For that reason, I was seeing like maybe the first integral should be 0, at least in my head, because the primitive of theta is theta squared and theta squared is 0. But that's my reasoning. Of course, that's a definition. That's a reason that it's just like that.
Okay.
For that reason, I was like,
yeah, but take it more as a definition because. Yeah, honestly, I cannot give you a better answer than just take it as a definition.
okay.
Yes, okay. Yeah, so Belovich conjecture was that this scale, we don't really know what's going on, basically, but we conjecture that the space-time gets a little discretized, and he proposed using a totally disconnected number field to describe it, in particular the Piatic numbers, and he applied it to the bosonic string magnitudes, which we have seen already. But a slight thing to notice is that he proposed both while using a Piatic spacetime. This is a very radical idea because, well, the Piatic properties don't really fit with our description of the spacetime. And also, I take advantage of what having here right now the drawing. Imagine that this little thing is in string, and as it evolves in time, we describe it with a two-dimensional surface. One dimension is the length of the string, and the other dimension is the time evolution. That is why we also deal in strings. We talk about two-dimensional surfaces. Yes, this conjecture motivated a lot of works, but pretty much all of them after Belovich conjecture, they treated the Piatic, it's two-dimensional, we call it the worldsheet of the string. And the works that follow, they did treat the worldsheet of the string as a Piatic string, but they embedded it in a real spacetime, which it's easier to work with in that way. And in the 80s, the general strategy was to, as you saw, take the amplitudes, the expression for the amplitudes, and write Piatic analogs of them. So, for example, you saw that the 4-point amplitude can be written this way over the real, and we just simply put a p here and we change the reals with the Piatic numbers. What this proved to be, it remained a lot of physical things that we want remain true, and it's much simpler to calculate. In fact, I think we did in the first few days. We calculated this but they're much easier to handle, and that's what motivated a lot of interest. Well, one question that we can do is there a Piatic string worldsheet? I mean, in the usual interpretation, as a student, just always look, what is in the Piatic string? This was answered by Subrodin, also in that time. He managed to write the string worldsheet coming back to the upper half, which admits a description in groups, and he just switched the R. Well, in the way he switched the R with QE, and he realized that this group is a discrete space called the Bruchatit string. It's a linked graph with loops and a balance of p plus 1 from each vertex, g plus 1 edges out. And we do the same thing. We define fields on this Bruchatit string. We embed it in the real space. We find an action on the Bruchatit string. No.
The microphone is working. Is in green, the line is green?
Yes. Can you hear me okay? Yeah.
So.
Okay. And so he was able to obtain the previous conjecture amplitudes, Piatic amplitudes, from this action using field theory techniques. So he proved that it was more than just a conjecture, an analog. He was able to define more. Well, from a physics standpoint, more rigorous. Okay, now we'll talk a little bit about the Piatic superstring. There are some previous attempts at constructing them, but basically they are also, they start from the usual Piatic superstrings, and they write, usual real superstrings, amplitudes, and they write Piatic analogs of them. This was done in some different works, and there's also, well, there are some recent works. Spinors is just another description we have for fermions. And there were some, well, people also calculated effective actions on the Piatic line. The boundary of the Bruchatit stream can be identified with the Piatic line. And if I tell you effective action, I just mean that the action written here can be found to be equivalent in a way to an action on the boundary, integrating over the Piatics. That's what I mean by effective action. Okay. In our work, what we're going to do is start from an action, from a suitable Piatic action, and try to get the same amplitudes for the superstring. Okay. Now, here is the action. The first term is the one, has been previously known. It's actually the one obtained by Subrodin, and it's actually the one that was present in Angela's talk. I just changed the name from phi to x. What we add is the second term, which is, well, we have the psi fields, which are Grassmann value, they are Grassmann fields. And here I have a bunch of definitions. Eta mu is the Minkowski matrix, diagonal matrix with a -1 and a +1 signs. And well, we have the properties of the Grassmann fields. We also have the Piatic sign function. This is, well, we can define a sign function over the Piatics, but it's fairly complicated. There are actually 3 different sign functions, although I will not go into the details. The action can be written in this way, where we take a definition of an operator acting on the fields, and well, the fermionic term can be written in terms of what is known as a twisted Vladimir derivative, which is a Vladimir derivative with a sign function. In general, it's a multiplicative character, but in this case, we take the sign function. And just for notation, if I write tau equals 1, I just remove the sign function or take the trivial sign function. Well, I will just introduce some notation. And the F will be like an integral kernel for the fermionic action. And I define an operator for the fermionic term, to be just a convolution of this function with the field. And if you see the mu nu sub-indices, I just mean that I have the Gauss-geometric multiplier. And in this way, I can write the action as these two terms. In a way, it is nicer because it is a quadratic action with just an operator in the middle. Okay. Oh, I can get the equations of motion in the usual sense as I described. We take perturbations of the fields. We take the standard approach. We subtract the unperturbed action, and we take it only to the first order. And from this, setting it to 0, we get these two equations of motion. Okay. I can also check for a supersymmetric transformation. If I take the variations and I write them in this way, and A and B are just constants, and epsilon here is an auxiliary Grassmann variable. And if I substitute this particular choice, well, basically you get this by trial and error, honestly. You substitute the variation, and you can prove that it is proportional to this term. And if we want it to be 0, we just need to choose appropriately A and B. We only have one equation, so we have one free parameter. We can freely choose one of the constants. For example, I think I chose a particular constant, and for example, this will be a supersymmetric transformation of our superstring action. Okay. Oh, there's also what is known as a superspace formulation. Superspace means just using fields and operators that have both a usual part and a Grassmann part or a fermionic part. For example, here I can define a superfield. Everything gets super in this space. With a usual field and a fermion field, and with an auxiliary Grassmann variable. I can also define sort of a super derivative, a superpolarized derivative using Grassmann variables. And with these definitions, I have some constants that are not determined right here. I will determine it in the next step. We can set these identities. Well, we can check these identities. The thing is that we want the action to be in this form. We want to write it in the same way: a superfield, an operator, and another superfield. And this gives us a restriction on where there are constants, but we also have, there is also some freedom in choosing the constants, so we can invoke another restriction. And right here, I also introduce the vertex operator, which is the usual vertex operator that we've seen for corresponding to the tachyon, which is really the same, but we have the superfield right here, and we are integrating over the auxiliary Grassmann variable. And if we use the restriction that I want the vertex operator to look this way, this completely determines the constants for our superspace approach. And then we can establish now the superfield and our super derivative. Just to mention, we can also find the Green's function for this super operator. Green's function just means the inverse operator. This is another name that we use. And in particular, we can show that it satisfies this equation. This theta minus theta prime is the Grassmann analog of delta. Okay. Now, propagators. Propagators is also another name we can give to the Green's function or the inverse operator. We want the inverse operators of these two operators that are previously defined. For the first term, it has already been studied in other papers, and it's shown to be this one. For the fermionic operator, we calculated using Fourier analysis, Piatic Fourier analysis, Well, here are the definitions, but we have seen it already. And basically, we want our Prince function, fermionic Prince function, to satisfy this equation. In Fourier space, this just means that they are the reciprocal of one another. So we need to take the Fourier transform, which, well, I can check that it will be equal to this, and with this constant over here. But this constant will cancel out, so I don't really care what the result is. We will write this. Oh, here we have a sign function right here. So that in general, it depends on which sign function we use. But mostly we are interested in this uppercase. Okay. Then we calculate the inverse Fourier transform after we take the reciprocal of the Fourier transform, and we get this result. And therefore, we have calculated now the Green's function for the fermionic operator in our action, which is given by this. This is the result. Okay. Now we want to obtain the amplitudes. As I told you, we have this vertex operator. This is just the standard vertex operator in superstring, usual superstring theory. This is a Grassmann valued field, and so we are going to use the trick that we previously saw to write it as in terms of an integral over Grassmann variables. We're using an auxiliary Grassmann variable, theta L. L is just the particular point where we are going to insert the vertex operator. And here we are going to use the generating function, as you saw, which is just our functional integral with the action. And we add some terms in here in the exponential, which are, these j's and k's are usually called sources. Basically, what we do here is we complete the square. We have here quadratic terms in x and in psi, and here we have linear terms, and we complete the square. Basically, and that's how we get these terms. This is the result after completing the square. After this normalization, this functional integration part goes away, and we end up with these two terms that are quadratic in the curves. And we use the Green's function, which are the inverse operators. And this is the general result. And now we are going to use this to insert the vertex operator. If you see, we wanted to obtain the expectation values for the vertex operators. And if we choose correctly our sources, this will be equivalent to inserting the vertex operators. So if we choose the sources in this way, we will be obtaining the expectation value of our vertex operators as the generating function with the appropriately chosen sources. And we will also integrate over the theta variables, because it's part of the how we describe the vertex operators. Okay. So to get a better more explicit expression for the amplitudes, here I just in this expression over here, if we insert these sources and we work out everything, we got a lot of calculation. We can simplify it to these two results, and then we substitute it in the generating functionals, and the generating function, and we get this result right here, which again, after some manipulation of Grassmann variables and the logarithmic function, we managed to write it in this way. A quick clarification right here, somewhere along the line, I have said S is equal to 0, which wasn't the definition of the Vladimir derivative. And I took the sign of -1 to be equals -1. Now, that doesn't always happen over the Piatic numbers, but I restrict to the case where it does happen. That's why I was always interested in the case tau different than epsilon, if you were keeping track of that. And this result is very similar to the Archimedean result. Okay. And now now I'm going to define the endpoint amplitudes for the Piatic superstring. It's just the previous insertion of the vertex operators. Well, no, sorry, the expectation value of the vertex operators. And I add here some factors of the sign function. This is necessary to have a certain symmetry that we want to have in physics. Conformal symmetry was mentioned in the Compian's lecture. If we insert this sign function, we recover the conformal symmetry. Unfortunately, we have to define it in this way to recover it. And therefore, we can now establish the endpoint amplitudes for the Piatic superstring. This is quite analogous to the Archimedean expression. Okay. And now to actually perform the integrations, it is necessary to go back a little bit and expand the fermionic part using the Grassmann variable properties. I told you they were linear functions, really. So we get this product. This is a variable product, but in the end, it's just a finite number of terms, which will make the amplitudes to be a certain number, well, a sum over some other amplitudes that are of the Cohen-Nielsen type. The only difference is that we will be changing the permutation that we have in the kinematic variables. The permutations come from the ordering that we have in the theta variables, and after integrating, well, it will give us a sign that it will give us a sign of the permutation depending on what order these theta variables appear. But well, in general, what I want you to know is that it is a sum of several amplitudes of the Cohen-Nielsen type. We can characterize it a little bit better. We will have this sort of kinematic factor at the beginning, and it will be multiplied by the actual amplitude. Well, it will be the amplitude will be of the Cohen-Nielsen type, except for the sign function, which I forgot to mention. That will actually change the results. We can write these types of amplitudes in this way by defining this function that depends on the permutation of the variables. It is just 0 or 1, and it will change by 1 the exponent in these two products. Okay, and now I'll tell you a little bit about what we can do with the conformal invariance. You've seen before that we basically fix frequencies. Well, this is the invariance under these Mobius transformations. We can check that it is, well, with this, if I perform this transformation, we can check that these products change in this way. And well, if you insert this in the amplitudes, you can see that it doesn't really change form. The form will be exactly the same in the y bar variables. That's why we say it is a symmetry. We need to use these conditions, which is this one's conservation of momentum, and it's just it's just the value of the k-square, which is related to the mass of the state. And with this we're going to be able to simplify the amplitudes. And again, what we do is we perform a type of Mobius transformation with choosing appropriately the constants A, B, C, and D, all the parameters. And we write it in this way. This will be our transformation. In terms of x and y's. We perform this transformation only in the n minus 3 variables. And this transformation actually is what, in a way, fixes the points to 0, 1, and infinity, which is just a convention to use the 0, 1, infinity. With this transformation, we can check that all of this, we check all of these identities and we see how the measure changes this way. I'm going to do it right here, but if you insert it in the amplitudes, where you actually get a factorization of the amplitudes, and we get this term, well, this factor, this is one of the factors right here, which is really the previous amplitude, but now we have changed, or well, 3 of the variables we are now integrating over. I think this should be an n-3 actually. This should be n-3. We have fixed one of the points to 0, the other to 1, and the other to infinity. But after you make the transformation, it simply doesn't appear over here. The factor that we get, there's a slight thing I should say. Well, in Dr. Compian's talk, if you saw carefully, maybe, there was a division by the volume of the symmetries. We usually tend to, we don't want the symmetries in our amplitudes because it would be like overcounting the system. It's a redundancy, and we don't want that. So we simply divide by the volume of the symmetric groups. But basically what that means is that we're going to ignore the factor that appears over here, and we are just going to well, we can redefine the amplitudes to be in this way after fixing the 3 points. Okay. Just as an example, we can set n equals to 4 and obtain the basic 4-point amplitude. This is in, well, it gets, this is the what you get after substitution. And again, these are well, like the usual bosonic 4-point string amplitudes that we've seen in other talks, except that we have these sign functions over here, and we have 3 of them. The sign functions actually simplify a little bit further. We get less terms than with the usual. That if we didn't have the sign function, we would get more terms. And after integrating all of this, we get, this is the result that we get. Well, the superstring 4-point amplitudes. Oh, well, it's worth noticing that this amplitude has been previously reported a long time ago, and these were the amplitudes that were constructed just as an analog, directly from the usual Archimedean amplitudes. They just took the analogs and they got the result. And well, what we can say that we did is that we obtained this amplitude from a more fundamental approach, starting with an action. Let me just give some conclusions. As I said, we described the superstring amplitudes, the Piatic superstring amplitudes, starting from a suitable action. We were able to find a supersymmetric transformation and also a description in the superspace approach. This is usual to do in the Archimedean string theory or superstring theory. And we obtained similar results to the Archimedean counterparts. And we also reproduced some previously reported results. And I told you that we had to do the unfortunate addition of some sign functions to recover a very important symmetry, which is conformal symmetry. But it is also another problem if this amplitude with the sign functions could be directly derived from a suitable action. I just leave here some references in case someone is curious. Over this Piatic string amplitude, these are some general references that you can see. And that's it. That's all. Thank you.
Are there questions or comments? Okay, it was a very nice talk. Thank you. Let's end the speaker again.
Thank you.
That
Todos hablan español.